Hey, okay, students. Hey, welcome to our next lecture. I'm just going to swing around to the front of the classroom and say, hey, we are without my cameraman today, so it's just me alone here with you guys. And so I've got the camera kind of zoomed in here on this one whiteboard, which is actually the same one that is used for the projector screen. And so we'll be kind of in a tight spot here for today, but I think it'll work great. I'll just have to kind of erase a lot and kind of pull the screen up and down a lot, but I think it's going to work. And so welcome to our second chapter on modern physics. The last lecture was on special relativity, and so this one here is our introduction to kind of the other big issue that shocked physics. Remember, I was telling you that there is a phrase we like to use, the 30 years that shocked physics. From 1900 to 1930, there was just some amazing discoveries and things that just seemed abnormal to us. And as I said in the last chapter, that kind of makes sense because we had never gotten close to the speed of light. And so as we kind of examined things with a little bit of an experiment and began to realize, and of course if you remember last lecture, it was kind of founded in the idea that the speed of light would look the same from every observer regardless of how fast they were going. And the experimental evidence seemed to point in that direction. So Einstein, in both his brilliance and his boldness, just made a bunch of logical conclusions and a very bunch of surprising discoveries that panned out to be correct after experiments. Well, we're going to see the same thing here today. So you enjoyed the last lecture, which I hope you did. I think just as equally you'll enjoy these next couple of chapters because they introduce us to this idea of quantum mechanics. And so I guess I will start by saying, okay, chapter 29, as I just said, its title is called Introduction to Quantum Mechanics. And so hopefully in this chapter we will begin to see, number one, what is quantum mechanics? Number two, what was the thinking in those 30 years, and of course even beyond 1930, but in that time frame, what was the experimental evidence that made scientists go down this road to try to say, well, the world's different than we thought it was with Newton's mechanics, and we've got to then modify it. And that's this whole idea. In fact, the other piece of this is, why is there even quantum mechanics? Because quantum mechanics is going to sound kind of weird at first. And so just like special relativity did in the last chapter, sound kind of weird, but hopefully begin to make logical sense if you're willing to accept the fundamental beginnings that the speed of light is the same for all observers, as the experiments seem to show. Here, we will talk about those experiments here and why we need quantum mechanics. I kind of like to put a little graph here on the board, and maybe graph is the wrong word. It's more of a chart, if you will, but a chart done in a graph form. And on the horizontal axis, I like to put speed, and up here on the vertical axis, I like to put size, and maybe I like to put a little dotted line right here, and then put in 10% the speed of light. And the reason for that is because we've learned, again, going back to last chapter, that all of our physics 110 and up until we got started in chapter 28 when we weren't going close to the speed of light, we were learning all about Newton and Galileo and Joule and Archimedes, and the list goes on. But this is often referred to as classical physics, because once we got past a speed of about 10% of the speed of light, and in order to keep the speed of light the same for all observers, we had to realize that there was more to our equations, and that was that big gamma factor. And we said, okay, so gamma equal to 1 is what happens here, but as you get 10% the speed of light, gamma now becomes 1.005, and that half a percentage point begins to show up in the experiment and becomes an important piece of understanding the science. And so there was kind of this dividing line. I suppose even maybe way out here I would put a solid line at the speed of light, because then we said, well, once we understood special relativity a little better, we said it takes an infinite amount of energy to go to the speed of light, so you never go to the speed of light, you just get close to the speed of light. And of course there's always this science fiction speculation about going faster than the speed of light, but definitely in the realm of science fiction. So our science tells us that we can't go to the speed of light, although we can get closer and closer depending on how much energy we want to put into it. Well, what I want to do in this little chart is kind of the same game. I want to put a little dotted line on the vertical axis, on the size part of it. Because what I want to introduce you today, and so just like last chapter, I hope you'll be kind of fascinated with this kind of the storyline and why we need, in this case, quantum mechanics, last chapter, why we need all these other gamma factors to go in there. And we're going to see that when you get to be about the size of an atom, the physics as we understood it just doesn't work right. It doesn't match. And so there must be more to it. And so just like Einstein did with relativity, we're going to look at people like Planck and Broglie and Schrodinger, and let me not forget Einstein also, as they begin to think, well, what's different on the small regime that begins to have an effect that we didn't really see when we were looking at big things. And so it's down here, let me just put a QM for quantum mechanics. And so it's down here that I want to introduce you to. What happens when we get really, really small? And again, as you will quickly see, the physics as we learn from classical physics just doesn't work. And so we like to draw these and say, all right, go ahead and use your classical physics if you're at a low speed and a big object. But if you're at a low speed and a small object, that's what I want to talk about today, the physics of the small stuff. Of course, this begs a very interesting question right here. What if you're small and going fast? And so here's kind of what we call our direct quantum mechanics. And so there's another name for you, but we won't go that far in this class. And so we'll just kind of introduce you to small things and fast things. So we've already seen fast things. Let's talk now about small things. And that's what we'll do for the rest of the semester, talking about small things and then some useful applications to it. All right, so with that said, I guess I will also say that let's cover here sections 1 through 6 of chapter 29. And so the section 7 and 8, you don't need to look at. It's kind of fun if you have some extra time, look at it. But in terms of homework and testing you, we just don't have enough time to do all the neat, fancy things here. And so we'll just say, let's call it a good at sections 1 through 6. Okay. So, with that in mind, let me just stay on this one board. Let me clean it off here and say, all right, let's look at the first step. We often call this the birth of quantum mechanics. And this is where the first player comes into play. This is Planck. And it kind of picks up in our optics that we just kind of wrapped up and finished from the last part of our classical physics stuff. And so I will call this the birth of quantum mechanics. Your author calls it Planck's contribution. Well, what did Planck do? What was his thinking? What was motivating his thinking? And kind of the best way to understand that is to look at a light bulb. And so if I take a light bulb that has some electricity running through it, And so it has a filament. So maybe my light bulb looks something like this. And then our light comes out. And so like I said, I'm going to take you back a couple chapters back into our optics. I even bothered to bring out this light bulb again. And so here is our light bulb with the filament hanging from it. And I put it on a power supply that I can adjust the voltage. And so I could maybe turn up the voltage, and it looks like I'm at about 20 volts. And I hope on the camera you can kind of see it begins to be glowing red. We would call this red hot. I wouldn't call it very bright by any means, but if I turn it a little higher, it's kind of turned a little orange. Now again, I don't know how the color balancing is coming out on the video camera, but I'm hoping you can kind of see it's not as reddish. So watch, I'll turn it down a little bit. And of course it's dimmer, but it's also a little more towards the red in color. I'll go high again. Let me go up to 30 volts. Okay, so here's 30 volts. A little higher. But it's a little more orange. Now, obviously, it still must have some of that red in it. In fact, it is beginning to kind of look even a yellowish, and so I'll turn it up more, and it's kind of yellow and more. You know, now it's getting kind of bright and hurting my eyes, and I don't know how it's coming out on the camera. But if I just keep going higher and higher voltage, and so the filament gets warmer and warmer. I mean, now it's so bright, if I try to look at it, it's even hard to say what color. In fact, I would probably say all the colors are there, because now it's what we would call white hot. Okay, and let me just turn that off and get my eyesight back here. Oh, yeah, that was bad. But it gets really, really bright. And so what I want to do is take a moment here and say, let's talk about that. Let's talk about that spectrum. And this is where a couple pictures from your book might be nice. Let me get my little laser pointer and turn on the display here. And so I started the book here at the beginning here, where it says Introduction to Quantum Mechanics. And if I scroll down to, looks like the third picture here, we've got a picture or a graph that is trying to represent what I was doing with this light bulb. And so Planck is looking at this. Planck is studying this, and he notices, and by the way, he wasn't the first. He's the one who gets the first correct answer. I think Rayleigh and another scientist named Jean were kind of studying this, and they said, this is the experimental data. And so let's talk about this. On this graph, on the vertical axis is the intensity. On the horizontal axis here is the wavelength. The graph is the intensity of different wavelengths at different temperatures. So he's got 3 different temperatures. The coolest temperatures at about 3,000 Kelvin, call it red hot. Then he goes to 4,000 Kelvin and eventually white hot at 6,000 Kelvin. And hopefully this graph matches kind of the picture we just saw with this light bulb, like when it was red hot, when it was only about 3,000 Kelvin, and I was at about 20 volts. When that little filament was here, if you look at the spectrum, it peaked at some value and then tapered off. And so the intensity in the red. Oh, and I guess I should point out on the horizontal axis, your author has put the wavelengths for the visible spectrum, all that optical stuff we just did. And if you remember, the wavelength of red was the bigger one, the 700 nanometers. Now, he's plotting this in nanometers. And so here's 1,000, and so 700 is right about here. See, and this 3,000 comes right here, and you're looking at the intensity of red. It's not the maximum in the whole spectrum. It looks like the maximum in the whole spectrum is just a hair under 1,000. So we would say the maximum would be in the infrared, but there is then some light in the visible, red being the most, and then tapering off, and you can see at the short wavelength, violet, there's really hardly any. And see, remember that, you know, your eyes are going to pick up those different colors. And in this case, since the red is the most intense, you might say it looks a little more red than anything else. You wouldn't say it looks pure red. And that's what this graph is showing. This graph is showing that you would have a variety of colors, but the most intense would be red, and you hardly have any violet. You might even say no violet. And so that way you're going to say, well, it's not white, definitely, because white would be this interpretation of my eyes where I have all the colors, and maybe all the colors at equal intensity. And so this is why we called it red hot, and this is why I kind of wanted to show it to you. It would look kind of red because even though technically all the colors are there, the red is the strongest. So then if I turned up the voltmeter, which I did, and then I went to, I think, 30 volts, it got a little warmer. And I was trying to make it at about 4,000 Kelvin, and that would be this curve here. Now notice it peaks kind of in the yellow or the orange. This graph looks more like it's peaking in the yellow. I think when I had it, it looked a little more orange. And so I would say it probably was peaking in the orange. And then as you look at the spectrum, there were other colors would be there. And so even though it was peaking in the orange, I would say the intensity of the red, and in this picture, they have it peaking in the yellow. I would say that maybe even the green and the red kind of have the same amount of intensity, but then it drops off, and the light blue and the dark blue, and then the violet, particularly the violet, there's hardly any violet. And so again, I would probably say there's not, you know, a full range of colors. It's not going to look white to me. It's probably going to look a little bit of orange. And again, not a perfect orange because it's got just as much red and actually quite a bit of green. And so it's got kind of this warm set of colors to it. And so it looks kind of warm, but it doesn't look white. It doesn't have all of them. Now, if you go even higher, you get up here and at about 6,000, this is the kind of the surface temperature of our sun. So this is kind of showing us the spectrum we would get from the sun. Then you would get almost equal intensities across here. It looks like it would peak somewhere in the middle of the spectrum, like a green or even towards a lighter blue. And then we got atmospheric conditions, and so by the time it goes through the atmosphere, it kind of peaks in the yellowish. Anyway, so we often call our sun a yellow sun because of that. But they're spreading out over here, and this would be a lot of intensity for all the colors. This is when it was hurting my eyes I was looking at. I was like, ouch, ouch, I can't see, you know, and it took me a couple of minutes for my eyes to adjust. It was just white hot. All right, so knowing that's the experimental values, and maybe interpreting this chart a little better. In fact, maybe throwing a fancy name out here, this is often referred to as black body radiation. And I know the sound black body radiation just sounds wrong when you're looking at the sun and say, hey, here is a black body radiator, and you're like, well, it doesn't look black to me, it looks really bright and it's white. Well, what we mean, if you remember from our optics, is black means that you aren't getting any colors. You know, so if like you close your eyes and even put a pillow over it, because, you know, even some light can get through your eyelids. So close your eyes, put a pillow, and go, what do you see? And I would say, well, you're not seeing any light. Yeah, and what color does that look to you? And so like we did in the optics, we called that black. And so many of our objects, like maybe the top of this red pen, it's red because it comes in, all the white light hits it and reflects off, and of course, only the red light reflects off, and so we call this red because it reflects the red. So when we call something a black object, what we mean is it absorbs all the light. we're not saying that it also can't re-radiate all the light, and that's the sun. The sun, if you shine a flashlight at the sun, none of that light will reflect off. All of that light will get absorbed by the plasma on the surface of the sun. Hence, the sun is black. However, it is so hot, it will re-radiate it in its own spectrum based on its temperature. So what the sun looks like has nothing to do with the light that's been illuminated on it. That's why we call this black body radiation. And so a light bulb and the sun and a candle, these are all referred to as black bodies. They're not that their color is black, but that they absorb all the light, and that what they look like, the light given off from them, has nothing to do with any reflection. And so be careful with that word, black body. Now, what I'm going to put here on the board then is a lot like the picture we just had. I'm going to put the intensity on the vertical axis. I'm going to put wavelength on the horizontal axis. And I'm going to kind of mention some work before Planck. As I said, two people, Rayleigh and Jeans, were the two people who said, you know what? The spectrum that we see that goes up and curves down, so I'll put the experimental value up here. So goes up, peaks at some value, comes down. And if you'll notice, all the ones did this, regardless of what their temperature was. It's just they peaked at different amounts and they had heights, but they all kind of had this overall pattern. So we refer to this as the black body radiation pattern. And so again, if it's a candle, the sun, they have this same pattern, although a candle and the sun are at a different temperature, so they peak at a different location, but they have this overall piece. And Rayleigh and Jones said, well, that kind of makes sense, because let's think about where the light is coming from. So let's go even further back this semester. If you remember, we said way back near the beginning about charges. We said that all material is made of these atoms. And these atoms are moving around and they have charges with them. And so as they move around, they would bump into each other, and that would be an electric field. And every time they bump, there would be a changing electric field. Now let's go just a little bit back this semester. Remember our optics. In our optics, we said that light is made up of electric and magnetic fields. And so magnetic field comes from moving charges, and the electric field comes from things like the proton and the electron. See, this is perfect. They're thinking, okay, I understand what's going on. You just take something that's really hot, like the surface of the sun. So I brought these bouncing BBs out here to kind of remind you. Here they are. I'll say this is them bouncing around. So if you could imagine these, it's kind of loud, so I'll turn it down. But if you could imagine these kind of being the surface of the sun, or the little spot on a candle, or the filament, that tungsten filament in that light bulb, then I would say as they're bouncing around, you might have a good intuition that you would get a spectrum like this. Because you would say, well, they're bouncing around, and some are going fast and some are going slow, but most of them are kind of going in a middle speed. In fact, we did this speed distribution, if you remember, back in our chapters of thermodynamics back in Physics 110. And the speed distribution looked a lot like this. And so Rayleigh and Jones said, well, that makes total sense. Except then they did the math. When they did the math, they began to put the mechanics of our thermodynamics and the bouncing atoms around, and they put it with our electromagnetics. And the math is pretty advanced, pretty complicated, so we won't run through it. But I do want to point out then that what they discovered is that the intensity should look a little bit more like this. I'll put it in blue. And what they ended up discovering is their understanding of mechanics, thermodynamics, and electromagnetics. They put all of their understanding together, calculating what the spectrum should look like, and it didn't match experiment. That's the real first point here. This is our first step towards saying something else is going on. If we take all the known information and we put it together and we calculate a spectrum that looks like this blue line, but in reality, blue line, but in reality, our measurements show the black line. This is our evidence that there's something more going on and something we don't quite understand. This is a golden opportunity for a scientist to think a little bit deeper, to investigate a little bit deeper, to use that fundamental idea that I called empirical science and say, okay, what's going on here? Well, what's so different? And that's the beginning of our quantum mechanics. This is why we give Planck the credit for the birth of quantum mechanics, because here's what Planck does. And again, the math is a little bit, okay, a lot of bit beyond the scope of this class. But Planck says that, all right, let me think about all the known physics that we know, okay? And let me just kind of look at the work that was done by Rayleigh and Jeans and say, all right, what did they do? And then what's missing? And that's always a tough question. I mean, you can't really ask, what is it I don't know, and figure out what I don't know. But Planck is very brilliant, like Einstein, but something interesting, he's not as bold as Einstein. And so I've been calling Einstein brilliant and bold. I would call Planck brilliant, but not bold, because here's what he does. He says, all right, let's take this group of atoms. And so here it is, these atoms bouncing around, or if you want, here it is, the filament in the light bulb. I get it really warm, the atoms are bouncing around, and I try to understand what's going on. And if I only do the work that Rayleigh and Jings did, I get the same results. And so Planck steps back and says, well, what would add to this? And he realizes, after kind of looking at the math, and I'll just do kind of a one-dimensional graph here of energy, and he said, if you look at the energies that the atoms have, if you restrict them to certain levels, maybe a good analogy of this is if you had a ramp that went up the side of a building, you could walk partway up the ramp and stop anywhere you want. But if you change that ramp into a staircase, then you're restricted to certain heights. You can't have just any height up. You either are stepping on the 12th step or you go up to the 13th step, but you really can't stand at a height that is 12 and a half. You're either 12 or you're 13. In other words, you're quantized. That's what that name quantized means. And this is what I want to introduce you just to the name first. What do we mean by this word quantum mechanics? And Planck starts it here, the birth of quantum mechanics. Planck says, I'm not going to try to explain why. I don't even know why. In fact, this is the part where, sadly, he's not bold enough. He's even going to say in his very famous paper, I don't believe this to be true. I don't believe that the energy is quantized. However, let's have a talk about it being quantized. And something interesting comes out with our statistics. And so, like I said, he's brilliant because he realizes that if you just quantize the energy level of the atoms, you will actually get the spectrum that we observe. That just gives me goosebumps. It's so exciting. It's like, this guy must be brilliant. How did he figure all that out? But on the other hand, he's not the boldness of Einstein. He just says, well, this has got to be wrong. This doesn't make any sense. The world can't operate this way. This is totally BS. But again, let's look at the math. It's kind of interesting. All right. So you can see where I'm going with this, that later on we're going to accept this quantum mechanics to be true. But at that time, the first one, Planck, is like, can't possibly be true. But I do want to tell you what we call then Planck's hypothesis. He just says, let's assume, without justifying it, without giving a reason why, let's just assume that the atoms are restricted to quantum levels. And so again, my analogy is, picture a ramp going up a building, change that to a staircase going up the building. And now your heights up to the building are limited in quantized numbers. So that's what Planck's going to say. Planck's going to say, I'm going to do all the work that Rayleigh did, and then I'm going to add one more piece, and that is to say that the atoms then are quantized. And so they have a particular spacing between each energy level. This spacing, he says, would be equal to some constant number times whatever frequency they're vibrating at. And so if you imagine a little atom bouncing around at some frequency, what you're going to say then is it would have an energy of some constant, which today we call Planck's constant in honor of his work, times the frequency. So this is where he starts. And so I guess that would mean that the lowest energy right here that an atom could have would be 1 HF. The next it could have is 2 HF. The next it could have is 3 HF. And so that's his thinking. Now it turns out he was almost right. Later on with Schrodinger, we'll learn here that instead of being some integer times HF, the energy comes out to be some integer plus a half of HF. So I don't want to dwell too much where Planck was a little off. And like I said, he was a little off. And so I'd like to give you what we understand today. And so let me just right here at the beginning give you the correct equation for the quantization of the atoms. But at least let's go through this storyline in Planck's thinking. And so you can see that he was off by a little bit, but it was close enough that he got some good results. And that's where we want to continue our conversation. Now, like I said, this number h is now referred to as Planck's constant in honor of him, but he is able to actually then take a look at his math and figure out what this constant would have to be in order to make that spectrum curve. And so he comes up with this number. And like I said, he just calls it h, and today we refer to it as Planck's constant. But you can see also the units here would be a joule times a second, because the frequency is in hertz, which is a 1 over a second. So when you multiply this together, this would give us what we need, the units of joules for how much energy does an atom have. Now, of course, the reason Planck never noticed this 1/2 is he really did not have the ability to look at the individual atoms. Remember, what he looked at was the spectrum coming from the atoms. And so his logical thinking was, if the atoms can only have these quantized values of energy, then when they give off their energy, when they give off the light energy, and that's something he can measure, they would have to go from one level to the next, to the next, to the next. And so as the atom lost energy, it would give off light, and the energy of that light would be HF. And then, of course, notice it would be HF even if they were offset by this extra 1/2. In other words, writing this in blue, we would understand this level to be 1/2 HF, and this level to be 1.5. I'll write it as 1.5 HF, and this level here to be 2.5 HF, and the next level to be 3.5 HF. And so as the atom loses its energy and gives it to the light, and if we're observing the light, there still is a difference of just 1 HF between each step. And so you can see why he was thinking that the energy of the atoms must just be an integer number of HFs, because as he looked at the light and he tried to figure out how to do the spectrum, they came in these quantized bundles of HF. Okay. Well, that's the first section. But before I kind of leave this first section, I thought it might be nice to run a quick calculation. And so I brought a laser pointer, actually a couple of laser pointers. And why don't I start with my green laser pointer to kind of give you a feel here. Where's my green one? Here it is. And so you can see it. I'll shine it on the whiteboard here. And so I'm shining it here, and I got this green light. If I look here, it actually says that the wavelength of this is 532 nanometers. So using this idea from Planck that the light then is coming in these little bundles, which I will refer to then as the photons of them, I could say that the energy of one photon is HF. Now let me remind you from our optics that the wavelength times the frequency is the speed. So I can get the frequency by knowing the wavelength. And then that's what I do know. So the speed of light is 3 times 10 to the 8th meters per second. The wavelength is 532 nanometers. If I put those into my calculator, 3 times 10 to the 8th, divided by 532 nanometers, I get a frequency of 5.64 times 10 to the 14 hertz. Let me then use that over here to figure out how much energy is in just one of these photons. So this would be 6.63 times 10 to the minus 34 joule times a second, frequency 5.64 times 10 to the 14 hertz. A hertz is a 1 over a second, so this is going to give me the energy in joules. So 6.63 times 10 to the minus 34 times the last answer gives me a value of 3.74 times 10 to the negative 19 joules of energy. So not much energy in one photon. In fact, it reminds me of last chapter that we had a unit called an electron volt that was very useful when we were dealing with small particles. And in this case, I would say small energies, and so have got this little new quantum piece I'm going to refer to as the photon, and say, all right, what's the conversion factor? Well, as we said, there was 1.602 times 10 to the negative 19 joules in one electron volt. And so I will divide that by 1.602 times 10 to the negative 19, and it's about 2.33 electron volts. And so now you can see why the unit of electron volts is kind of nice for these photons. This is how much energy one photon has. And again, not much, I agree. Now, if we come back and read it a little more detail, not only does it say its wavelength is 532 nanometers, but it says its output power is 5 milliwatts. So the way you get 5 milliwatts is because you have a lot of photons. And so kind of the visual picture I want you to have here is if this is kind of my laser beam here, then what's coming out of this are a bunch of particles that I will now call photons. And of course, one photon, as we just said, has this much energy, or this much. Again, not much. However, they're traveling really fast, and so there could be a lot of them crammed real close together, and so you could end up getting quite a bit of energy. Now, 5 milliwatts may not sound like a lot of energy, and I suppose total energy it is not. In fact, I could, take the laser beam and shine it on my arm, and that 5 milliwatts, I guess, would be warming my arm, and I'd go, well, I can't even tell. I mean, it's not like it's hurting me. It's not like I feel it getting warm. And it's certainly not like it's cutting me or damaging me. So, yeah, I would argue that 5 milliwatts is not that much energy. However, I would also say it is concentrated into a pretty small circle. And so maybe I'd say the intensity is quite a bit, which is why we shine it here on the board and use it as a pointer, because the intensity is actually quite a bit. And we just need a few of those photons to bounce off and go to our eyes. Okay, I shouldn't say a few billion photons to go to our eyes. But that's what I'm getting at. I'm kind of curious here, is how many photons would this be? And so let me go ahead. I'll leave the answer here to the energy alone for just a second and say, if I wanted to know a little bit more about how many photons are here, I might do something like this. I'll change my equation. Energy total then would be HF, which is the energy for one photon, and then times N, and be the number of photons. And so notice here, I'm trying to give you a new way of thinking. Instead of thinking of our light energy as an electromagnetic field, as we did before, and as I'm trying to introduce you and have you cross the line from classical physics to modern physics, I'm trying to say, well, I'm going to change my perspective. I'm going to stop looking at light as a wave and start thinking of it as these tiny particles. Now, again, I'll say that Planck deserves a lot more credit than he often gets because he did this. But again, he also made it very clear he didn't really think that's how nature was behaving. Now, I'll show you some other work that is going to lead to that Planck should have been a little more bold. And that's coming up. But I'm going to run with Planck anyways, even though he wasn't bold enough to say this. I'm going to say, let's stop thinking about our light as being waves and now think of them as little tiny particles, which we will call photons, and they're traveling at the speed of light. They're a little, as Einstein put it, quantum of energy. The phrase photon didn't come around till after Einstein, but he calls them the quantum of energies. And so these little quantum of energies, I'm kind of curious how many there would be in this laser pointer as I shine it here on the wall. So what I'm going to do then is divide both sides by time. See, because right there is saying the total energy per time. That's the power. And it says right on here that this is 5 milliwatts. Now remember, a watt is a joule per second. So that is the total energy coming out of this laser pointer. If I group together the number of photons per time, and so like the number of photons per second, that's what I'd like to know. Those two together. How many photons per second are coming out of this as it shines across the room? And then, of course, this HF is this number here. It is the energy of one photon. So this is 3.74 times 10 to the negative 19 joules. And of course, you'll see the joules cancel off. And so when I go to solve this for number of photons per second, I'm going to get some number per second. And that's how the units work out. And so if I grab my calculator here and on this side put 5 times 10 to the negative 3 and then divide it by 3.74 times 10 to the negative 19, I get 1.34 times 10 to the 16 photons per second. So there's a lot of photons here. And so these are little tiny objects, if you will. That's kind of how I want you to think about them, or at least for a moment. And we'll kind of do better as we move along here. But I thought a quick calculation of the energy per photon and then how many photons per second would kind of help solidify this kind of first step of what's going on in Planck's thinking. And like I said, he justifies it because he uses that to explain the black body spectrum. And so he publishes his results, and he does say, as I mentioned, that this is a very interesting feature, that it does explain the black body radiation, but he's also quick to say that this couldn't possibly be right. There must be something else. Kind of a plea, say, somebody else think about this. So this is 1900. So we call 1900 the birth of quantum mechanics because, like I said, this is the first time somebody used the experimental evidence to show that the physics we currently understand doesn't explain what we observe. And also that's when Planck says, well, let me throw in something that we don't know about, but yet seems to explain the experimental evidence. And so we just follow that empirical science. Well, this is out there for about 5 years. And in 1905, Einstein re-enters the picture here. And so this is called the photoelectric effect. And it is what Einstein gets the Nobel Prize for, despite all the other great things he did. This is the one that the Nobel Prize committee finally zeroed in on and said, okay, let's give him this one. Because all of his papers of 1905, there's 5 of them, or at least 4 of them, are all Nobel Prize winners stuff in them himself. So, not a surprise that Einstein uses his brilliance and his boldness. Okay, so here's where Einstein comes into the picture. Now, maybe before I look at Einstein's work, we better understand what is this thing called the photoelectric effect. So, as the name implies, photoelectric, it has to do with electrical charges and it has to do with light. And so during the late 1800s, scientists were running in experiments that were something along this line, that you take some lights and they tried light of low frequency, high frequency, low intensity, high intensity, and they shine it on different materials. They did aluminum and beryllium and sililium and the whole list, silicon, some mixture of other stuff, some alloys. And there seemed to be this interesting effect that when conditions were right, electrons that were in your material, why don't I just say aluminum for a moment, would get ejected out. In other words, somehow they absorbed the light, the energy from the light allowed them to come out. So that is called the photoelectric effect. And so as the electrons came shooting out, of course, then the scientists would measure, first, did they or did they not come shooting out? And then second, if they did come shooting out, how much kinetic energy do they have? And how many of them come shooting out? And so after playing with all these parameters, and I'll say it again, small wavelength, big wavelength, low intensity, high intensity, different materials, whether the electrons did or did not come out, if they did come out, how much kinetic energy did they have, and how many were they? And they begin to see kind of a general pattern, but most interesting, it was a general pattern that kind of made no sense to them. With the known physics at the time, it just didn't work right. It was actually kind of just almost backwards of what you thought should have happened based upon the known physics. And the known physics at the time is the physics that you've learned so far. In fact, your author does a really good job here of listing these. And so let me just look at your author's work here. And so if I scroll down past section 1 and into section 2, maybe I'll pause on this picture here because this is the little experiment. It's in a glass chamber, and I didn't put that in my drawing, but I hope it becomes pretty obvious. You couldn't have any other air molecules around, so all this has to be done in a vacuum. And so they put the little piece of aluminum or whatever they're studying in a glass tube, suck all the air out. And that needs to be a clear glass because you're going to shine light inside. And then you have to have other things in there to kind of measure, did the electrons get ejected or not? If they did, how fast, how many? And so that's kind of what all that stuff is there. So without spending too much time on the actual detailed experiment, let me scroll down. I'll pause on this figure. So this is what I was saying earlier, that, hey, maybe a better way to look at a flashlight, or a different way, I guess I shouldn't say better, a different way of looking at the light coming from a flashlight is that there's a bunch of particles called photons. And each photon probably has a little different energy because there's a bunch of them with different frequencies. That's the different colors. And so red has a particular wavelength, and so it has a particular number of photons. And green, what we calculated, has a particular frequency. All right. But getting then to the main part of this experiment, and I put it at 150%. Maybe you guys can see it a little better on the video here. But I know you have the book, and so look in your book, and here's what your author says. And the first two kind of go together here. It says here, if we vary the frequency of the electromagnetic wave falling on the material, the photoelectric material, we find the following. We find that for a given material, there is a threshold frequency, F naught, where the electromagnetic wave is below which no electrons are ejected. In other words, and we're going to call this a cutoff frequency, if you try different frequencies, if you're below some value, the electrons don't get ejected. But if you're above some value, they do. Now, the reason this is problematic is if you think of these as the classical wave, and I'll just pick up this object as if it was the electron in the material, so I'll put it on my hand. And if the wave comes in here and is made of an electric field, it's going to interact with this electron. Because remember, the electron is charged, and in a classical model, the wave, the electromagnetic wave, the light wave is this electric field. And so it's going to make this electron move. And maybe when it first hits it, it moves it to the left, and maybe that's not enough to break it free from the atom. Because you got to remember, this electron wants to be hooked to the atom. Remember, the atom has a bunch of protons inside of it. So again, if I'm picking on aluminum here, there are 13 electrons of aluminum and 13 protons. And so this is the outer one. It wants to stay with the aluminum. Again, because aluminum has a nucleus. The nucleus is positive. Now, it could get pushed off if you hit it hard enough. So the early scientists here are looking at this saying, well, if you hit it with a particular frequency, whether it be a low frequency or high frequency, you should eject them, because as they go back and forth, if it's a low frequency, you'll just kind of go back and forth until it builds up enough energy, and each time it gets more and more energy, and eventually it breaks free. And so it shouldn't matter whether it's a low frequency or a high frequency, it should break it free. But as I said, that's not what they saw. They saw that if you were below some value, and it didn't even matter what the intensity was. You might say, well, maybe I'll just give it more energy, so I give it more intensity. You would think it would rocket harder because the electric field would be stronger if you gave it more intensity, and that would break it free. And that didn't happen. And so again, I'm trying to give you an experiment that should be bothering you from the physics you understand right now. This should bother you. What do you mean it doesn't matter? Or it does matter what the frequency is? My understanding of the charges, what I just learned in my physics class, says it should just rocket back and forth, and if you increase the intensity, that means the electric field's stronger, so that should rocket even harder, and it should kick it off. And so it should kick it off based on the intensity, not based on the frequency. Now, I get how it might then take a while to break free, because if it was like a low intensity, the field wouldn't be very strong, so it would rocket back and forth each time, giving it a little more energy, but eventually knocking it free. So that should be your thinking. That certainly is the classical thinking. And that's what the scientists at the time were thinking. But that's not what this experiment showed. All four of these really, really bothered the early scientists. And so like I said, here's that first one. That first one says that there is some threshold frequency. If you're less than that, it doesn't eject them. More than that, it does. And that was just weird. I kind of touched on the second one here. The second one says here, once the electromagnetic radiation actually falls on the material, the electrons are ejected without delay. In other words, there's not this situation that you might have thought with a low frequency and a low intensity. If they slosh back and forth, it builds up and it builds up, and then they get ejected. And so there might be a waiting time of 20, 30, 50, 100 nanoseconds, or even microseconds, maybe even seconds. But there should be some kind of delay when the intensity is low. And there's not. Does that even make sense? And I hope you're saying, no, from the physics I understand, that does not make sense. And again, you're kind of in the same boat as the early scientists, going, that's crazy talk. What do you mean there's no delay? How's that even possible? And that's why we're studying this, because there's something else going on. There's something more you haven't been exposed to, although you kind of have, because we just talked about Planck. Okay, so look at number 3. Number 3 says the number of electrons ejected per unit of time is proportional to the intensity. Per unit of time is proportional to the intensity and to no other characteristics. In other words, how many electrons seems to be connected to the intensity. I would have thought that would have been related to the frequency, not the intensity. So it's backwards. And look right here. If we vary the intensity of the electromagnetic waves as measured by them, the electrons, we find that the maximum kinetic energy of the ejected electrons is independent of the intensity. And again, if I'm kind of imagining the physics that I understand, and so I'm like, I'm this electron, and here comes this light, and if I'm thinking of it as this electromagnetic wave hitting me, I would, rock back and forth till I got enough energy to eject. So there's the time delay, but that doesn't seem to be happening. But also, if you just increased the intensity of that, in other words, light has more energy, it means it has a stronger electric field, in my old thinking, then as it hits me, I would expect that it would kick me out and give me a lot of speed because it hit me with a really strong electric field, and so I should go shooting out. And so I would think that the kinetic energy of me getting shot out, this electron getting shot out, would have to do with the intensity, and that's not what happens here. The kinetic energy seems to be independent of intensity. See, just the reverse. You increase the intensity, you get more electrons, not faster. I would have thought faster electrons. So what's really happening? Well, like I said, here's where Einstein comes into the picture. Einstein says this. He says, we can explain this. We can explain all four problems with one answer. In other words, all of these four things that you don't understand, there's one simple answer to it. And let's go back and look at the work by Planck. See, Planck said that the light is not this electromagnetic wave anymore. Now, I want to say that a little bit careful because before we finish this chapter, we're going to use the phrase duality. And so we're going to see that light could be treated as one or the other, or both. It's both at the same time. But let's do this same thinking of this experiment, but think about the light as being little packages called photons. And remember, each photon has a value of HF. And so, like I said, here's Einstein's brilliance and his boldness, because he's just going to say, yep, the world is quantized. No doubt about it. No questions. Does this seem weird? Yeah, so what? But the world's quantized. And so just like he does with special relativity, he's going to do here with the quantum mechanics. He's going to be both brilliant and bold and just say, yep, the experimental evidence is very obvious. The world is quantized. Why is it quantized? Well, at this point, he doesn't have a really good answer for that one, but he just says it is. Because watch this. If you think about the light coming in now as little chunks of energy, as I said, Einstein called them the quantum of energy, so photons. And these electrons are connected to the aluminum atom by what I'll call Be, a binding energy. You see, it's one photon that is going to come in and hit one atom. And if that photon does not have enough energy to break the bond, it won't get ejected. And so that means there are photons that have lower energy than the bonding energy. That means there's a cutoff frequency. That means if they're below that, you won't break these free. It doesn't matter how many you have. You could turn up the intensity. And so now the intensity would be the number of photons per second. That just means you have more photons, which you're going to hit more atoms. But every atom you hit, one photon to one atom, every connection you make does not have enough energy to break it free. And so by turning up the intensity is not going to break them free. It's turning up the frequency. See, that's the total reverse of what I would have thought if I thought of it as a wave. And that's what Einstein's trying to say. If you think of these as little tiny photons, I can explain to you why there's a cutoff frequency. And that's his brilliance. It goes on to say, I could also explain why there's almost no delay. Because when these photons come in and they hit, they either have enough energy right then or they don't. There is no sloshing around. There is no building up of energy. There's no need for a time delay to actually build up enough energy to break the bond free. It doesn't happen that way. It hits it, the photon is gone, it gives all of its energy to the atom, and it either ejects it or not right away. And so again, looking at these as quantized, you have an answer for problem number 2, why there was no delay. That totally makes sense. And like I said, it's totally the reverse of what you might have thought if you were just thinking of it as a wave. Of course, this also explained, let's see, what was the other one? That their kinetic energies, when they get ejected, were connected to their frequency, not the intensity. See, in the old way, you would have said, well, more intensity has a stronger field. The field would eject them with higher kinetic energy. Then that didn't happen. And Einstein's saying, of course not, because what would happen here is the kinetic energy is really any energy that's above the bonding energy. Mathematically, I would write it this way. A photon comes in with an energy of HF, and the first part of the energy goes to breaking the bond energy. Another name for this is what Einstein used. He called it the work function. And so he says, look, the first little bit of energy has to break the bond. It's the work function. How much work does it take to free the electron out of the aluminum? And whatever is then left over is the kinetic energy. And so you might say then the kinetic energy should be equal to this HF minus the bonding energy. And so a graph of kinetic energy versus frequency, I guess, would have a slope of h and an intercept of negative bonding energy. And of course, you would never see them come free. And so if you were to plot the kinetic energy of the electrons versus frequency, there would be some cutoff frequency, where below that frequency they don't get ejected at all. And then as the frequency increases, so does the kinetic energy. And so again, totally the reverse, that the kinetic energy depends on frequency, not on the intensity, as the classical model would have told you. And so this was number 3 or 4 there in our chart. And the other one, either 3 or 4, was how many electrons. And again, in this model, we could see that the number that actually get ejected would be based upon how many photons you have. And that is the intensity of the beam. So the intensity of the beam should determine the number of photons, as the experiment shows. But in the classical model, it's the reverse. We would think that the number that get injected is related then to the frequency. And again, that's not what you see. This is a long way of me trying to do a couple of things. Number one, trying to give you another experiment that is verifying that the world must be quantized. And throwing into the mix Einstein, because Einstein is not only brilliant, but he's bold. And he takes the work done by Planck and he says, you know what, Planck had it right. The world is quantized. Let me prove it to you. Here is an experiment. And he explains this experiment and boldly says that where Planck fell short, and says the world is quantized. We can have a debate of if that makes sense or if you feel comfortable with it. That's fine, but that is not how science works. Science works based upon the experiment. If it doesn't make you feel comfortable, we really don't care. We don't care about your feelings. Sorry, I don't mean that in a mean way, but we really don't care how you feel about the science. We just care about what actually happened. And that's Einstein. He's like, look, I'm sorry you don't feel comfortable with this. I'm sorry you don't feel comfortable with special relativity. He even says, I don't even care that you don't feel comfortable. This is what the experiment evidence seems to indicate. And so now we have really when it gets accepted. And so in 1905, this is when quantum mechanics seems to be accepted, or the start of when it seems to be accepted that, yeah, this is the way the world works. Now, it'll take until de Broglie before we kind of get a feeling of why it works and an understanding of why the world is quantized. And so we'll get to that soon. But at this point in history, we just accept that it's got to be real. And so this is also a nice step. It can give me the energy. And we're going to do a lab on this. We're going to do a photoelectric effect lab. And we are going to then measure the energy and the frequency. And we're going to get a bunch of data points like this. And we're going to then measure this and get its slope. And as I said, you can see that this F is the equivalent of the x-axis. This minus BE is the intercept. And this H then is the slope. Or maybe I should write it as that. Because the kinetic energy is the y-axis. So this is the equation of a line where the slope of the line is Planck's constant. And that's why we do this experiment, so we can collect our data and we can get then a slope. And from that slope, we can get the value of H. And so there's our second experiment. Well, let me keep going on here, because along comes a third player. And then the fourth player will be our de Broglie I already mentioned. But our third player here is Compton. Okay. And so let me clear off the board here. And let's look at the experiment being done, or I should say experiments being done by Compton. And Compton runs this experiment. It's probably easier to show you on a picture from your book. And I'll say it quickly that you got to remember that Compton follows Einstein. Not sure how many years. This might be 7 or 8 years later. And by that time, science is accepting that the small little world of energy is quantized. And we just don't see it on the big world because the quantum levels are so small. If we go back to my analogy, remember I said if we had a ramp that went up the side of a building, we could stop anywhere on the ramp and we would say our height is not quantized. But if we turned it into steps, then we have now just quantized our height going up the side of the building. And we could either stand on the 12th step or the 13th or the 14th, but we can't be 14 and a half. We can't be 14 and 3/4. We're either 14 or 15 or 13. Hence the name quantum mechanics. And that's what we're saying. But if these steps are really small, then a big object like myself might see it as a ramp and go, oh, they're not quantized. I could stop anywhere on there. But if they're little tiny steps, an ant trying to go up that ramp would actually go, no, they're quantized, right? An ant would go one step, oh, next one. And then I got to take a step up, oh, the next one. And I got to take the next one, oh. And that's my added picture to this, that the world really seems to be quantized, but we, in the big world of big objects, we don't see these individual steps. They're really too tiny for us. And that's that correspondence principle I was telling you about in the last chapter. That would be equivalent to the gamma factor. It's hard for us to understand this gamma factor because we live in a slow world where gamma is close to 1. And if it's 1, we just pretend there's not another factor in there. It's not until we got close to the speed of light where the gamma factor began to be something different of 1, where we begin to realize, wait a minute, our equations aren't matching what our experiments give us. Something more must be happening. And so I'm trying to say the same thing, that this world is then quantized. But these energy steps are really tiny. And so us in the big world, we just see it as a ramp going up the side of the building. We go, oh, there's any value you want. But I'm trying to say, no, you can't. This is what both Planck and Einstein, and of course we're going to add to this with Compton and de Broglie and Schrodinger, they're saying, no, that's not really how the world is. The world really is quantized, although they're little tiny steps. So if you're on a big world, if you're building an international space station and you want to treat the energy as being continuous, go ahead, it's fine. Because the energy steps are so small, they're not going to make a difference in our engineering. And so if you're building a car, you can do classical physics. But if you get down to small energies, where the amount of energy you're working with is relatively to the size of the step, you've got to include the steps. And so from an ant's perspective, going up this ramp, going up the side of the building, they would see it as a staircase, but I would see it as a ramp. And that's what I'm trying to say there. So The experimental evidence is very clear. They're quantized. But they're small little values, and so us big things would go, nah, they're not quantized. And so that's the important piece I'm trying to illustrate. We only have to worry and think about the quantum on small scales. And so that's why we haven't been doing it early on in our physics, but now we must do it. And for those of you who've already taken chemistry, know that almost right away when you start doing your chemistry, you talk about quantum mechanics, because you're like, well, everything you do from the very beginning is on the small scale, and you just can't really understand the nature of chemistry without including the nature of quantum mechanics. It just doesn't make any sense. And so you get exposed to quantum mechanics. In fact, now that I think about it, most of you, I probably didn't even need to explain the word quantum mechanics to you, because you've been exposed to it. Now, obviously, there's quite a few of you who also haven't taken chemistry, so I want to make sure I start from the perspective that you haven't been exposed to the word quantum mechanics. But that's why, like I said, until we get to these really small energies and what we're talking about now, we didn't really need to think about quantum mechanics. And that's why in a chemistry class you got to do it right from the beginning, because that's all you think about is little tiny atoms hooking together and making your interactions. All right, well, let me continue on to the third player. The third player is Compton. And Compton, as long as I'm passing by this chart, I kind of like how your author said, let's calculate a bunch of energies per photon for all over the electromagnetic spectrum. And so he puts the visible ones here. And as you know earlier, we did the green one and got that 2.43 electron volts. And then over here, he does things like microwaves and radio waves. And so they're going to be lower than that. And then over here, you'll get the higher ones. And this will give me a chance then to kind of point out the effect, kind of like a photoelectric effect. But since you guys are in the life science, when this photon comes in and it hits, say, a DNA molecule in the skin, and it hits it, if that photon doesn't have enough energy to break the bonds between all the DNA until that double helix, let's see, I guess an A hooks to a T and a G to a C, and then there's the pattern. But there's a little binding energy between the A and the T and the C and the G. And if that photon doesn't have a high enough frequency, it doesn't matter how many photons you hit it with, it will not break that bond, and therefore it won't do any damage to your DNA. And so that's, I would call, kind of a positive result of this quantum nature. Whereas in the old school thinking, you would say, well, if it's a bright enough light, it'll destroy your DNA. But no, it won't. And so fortunately, these bonding energies of the DNA, are more like in the neighborhood of 3 electron volts. 4 electron volts. Meaning that if I were to take this green laser again and shine it on my arm, there is no danger, no matter how intense this laser is, that it'll break my DNA. And which oftentimes leads to problems like cancer. Nope, that won't happen. Now, it could be so intense that the total energy warms it up and maybe even boils the water inside the cell and therefore kills the cell. Boils, pressure builds up, the cell pops. And so I could damage a cell in that sense. And fortunately, my body has a mechanism to build new cells. This would be no different than cutting myself or burning myself. I just kill the cell and they grow back. But it didn't change the DNA. But at a high enough frequency, that could damage the DNA. And so that occurs up here near, like I said, that 3 to 4 electron volts. And so it's the violets and the ultraviolet that are above what we would call the cutoff frequency for damaging DNA. And so shining ultraviolet lights on my skin can damage the DNA. And hopefully when that happens, like when I'm in the sunlight and it damages my DNA, that the cell just kind of dies off and does its own natural thing and doesn't lead to anything bad. But after long exposures, things can happen, and then we get skin cancer. And so that exposure, or if you get exposed to X-rays, and again, it would take quite a few X-rays. So if you just break your arm and go into the doctors and they take a picture of your arm, that's not considered a health issue. I mean, those photons are enough, and they probably did destroy a few DNA ones, but again, not in a way that your body can't handle that and correct it and fix it. But if you did this a lot, I mean, if you had an X-ray taken every day, or if you are working as a technician in an X-ray lab, you know, you're exposed to those X-rays every single day. You're not directly in the camera, but the scattering of the X-rays in the room. That's why I always find it interesting when you go in there with, you got a broken arm or a hurt ankle or something, and you know, you're playing basketball, rolled the ankle. They want to know, did you damage it? They go in there, and so I'm sitting there, the rolled ankle, put my foot under the little X-ray machine. They come down, and the technician goes, okay, I'm going to take a picture, but I'm going to take the picture when I'm out of the room. And they go out behind this safety wall, and they push a little button back there. And I just sit there going, well, wait, what? How come you go behind the safety wall and I got to sit out here getting exposed to the X-rays? Is this really safe? And it is. It is safe. It's such a small quantity. I just do it once or twice or maybe 3 or 4 times because I keep rolling my ankle. But the technician, they've got to do that for every patient all day long. And so they might take, 20, 30 pictures in a day, and they got to do that every day. So that's a different story. You could say the same thing about pilots and flight attendants. Because our atmosphere does stop the cosmic rays, and so us down on the ground are kind of safe from that. That's the whole ozone worry, that the ozone helps protect that, and if we put chemicals in the air and get rid of the ozone, what's that going to happen at the ground level? We'll have more ultraviolet light, and we'll have higher cancer rates. Fortunately, we've done a pretty good job of reducing the ozone layer, and so decades ago it looked like an environmental problem. Now it doesn't get much attention because we've changed our freons, and that was the biggest factor. We still have other chlorine issues. But anyways, the ozone's doing much better, and it looks like long term it's gonna repair itself. So we don't, like I said, talk too much about that anymore. But what I am trying to say is those that spend a lot of time at high altitudes will get exposed to that. So you take a plane flight, you get exposed to a lot more radiation up there than you do back down here on the ground as you're flying at 35,000 feet. Now again, most of us just fly, at most 2 or 3 times a year, and that's not a big deal. But if that's your job, if that's your career, they keep track of that. They keep track of, what altitude, how long have you been up there, and so that they can keep track of, how much you've been exposed to over your lifetime. And so it's a health concern for pilots and airline assistants and up there. Anyways, I did want to then just comment with this picture up here, how each of these photons is more and more and more energy. In fact, gamma rays is so much energy. This is the kind of thing you would find in a nuclear reactor, and it's got so much energy. It doesn't take much exposure, and that will just rip apart DNA, and you'll have problems right away. And so radiation poisoning and death occurs in a short amount of time for these really, really high energy photons. In fact, it's kind of why I brought this one out. Here's kind of a fun one. I've got some liquid. Let me not get into the details. It's not DNA, but it kind of shows that same effect. If I hit this, molecules in here, and it's not water, if I hit them with photons with enough energy, they will rip apart, and then when they come back together, they will actually give off that same amount of energy that ripped them apart. In other words, they will be giving off light. They will glow. We call this a fluorescence. It'll look like it's giving off light. Look, you could probably see it really well. Let me get the green laser beam. And I'll just say that the green one is not enough. If I shine the green through here, you might not see anything. I'll just kind of show you the green's coming in and the green goes through and comes out and it goes right through the clear liquid. And I would say that it hits the molecules but isn't enough to tear them apart. And if they don't tear apart, that means they don't pull themselves back together to give off another photon. They just go right on through. And I can't get the camera to move, but over there on that far wall then there is a green light because it just goes right through. Maybe a little bit of the photons bounce off. I can actually see a small speck of green coming through there. Maybe you see it on the camera, but watch this one. What if I increase the energy per photon? Let me find my violet one. And so here's my violets. I don't even know if you can see it on here. The intensity is not very great, but the energy per photon is, because it's on this end of the spectrum. It's on the end that has enough to do damage to these molecules and actually rip them apart. And of course, once they rip apart, you'll have a positive and a negative, and so the molecule wants to come back together. And in the process of coming back together, it gives off that energy and it gives it off as another photon. And so you'll see something very different here. You'll see it come through, and of course, again, you can't see the far wall, but I think you can see the path that it takes because it's ripping those apart and then they're coming back together. And I don't know if you can also see this on camera. I hope it stands out, but the color on my hand here, or the color on this white paper, is more of a violet, and over here is a little more of a blue. And so the photons they give back are a little less energy. So it's not like it gives off exactly the same energy that ripped them apart. And so it's a little more blue, which is a little bit lower in frequency than the violets. And that's kind of what I thought I would point out in terms of trying to connect this maybe more towards you guys in the life science instead of the photoelectric effect, which is used like in copy machines, which I better not take the time, but that's a fun engineering question I do with my engineering classes. You know, how do you build a photocopier? And it uses the photoelectric effect. And for you guys, it's probably more about the life science and the interaction of the light with the material. Oh, photosynthesis is probably a good one. And so same idea, that you want to hit that, you want to give its energy to it, it's quantized, and that's why in the photosynthesis process, there's actually two mechanisms, one involving an energy near the red end of the spectrum and the other one near the blue end, and that's why really green light doesn't do any good for plants. It's just there's nothing useful for that amount of energy. That's why they reflect it, and that's why they look green. So plants look green because they don't want that green light. It's always a fun elementary school science project is to grow a plant under green light and see what happens, because you know everybody goes, oh hey, it's a plant, it's green, isn't it going to love green light? It should grow really well. So you put a plant under a green light and put it under a blue light and put it under a red light, and you'll see that the green one dies. It just doesn't have any more energy source in there because the energies don't match. And that's really what we're getting at here. All right, well, let me continue on with our history and our science here, because there's a little X-ray picture. There's an X-ray tube. There's an X-ray spectrum. But I want to look at what Compton did, somewhere in here. Where is Compton? Right here. And so Compton runs this experiment. He says, okay, now that we've kind of accepted that the light coming in is quantized, he already starts with the idea that I'm going to think of these as photons. And so he shoots them not at, say, aluminum like the photoelectric effect, but he shoots them at free electrons. So he figures out a very clever way, that's why he gets a Nobel Prize, of how to strip off electrons from mirror materials, kind of get the electrons to float in his little chamber so he could shoot photons at them, and he tries different wavelengths, include a lot in the X-ray realm. You'll see why he sees the result better in the X-rays. But he shoots them at this electron, and he discovers something quite interesting that I want you to see here. And that is that the photon comes in, hits the electron, bounces off, and we don't lose the photon, but when he takes his measurements of this photon, he discovers that it has a different wavelength, a different frequency, and therefore a different energy. Now that's not too big of a surprise, because when he looks at the electron, he sees that the electron starts to move. Okay, and knowing conservation of energy, he goes, well, the electron has to get its energy from somewhere. It's now moving, and so it must have got it from the photon, and so the photon must have shifted to a lower frequency or a longer wavelength in order to give the electron energy. That totally made sense. But what bothered him more was the issue of momentum. You see, this electron, when it starts to move, not only now has kinetic energy, but it also has momentum. Where did it get its momentum? I get the energy. Einstein and Planck reasoned out the energy quite well. But Compton's saying now, they didn't say anything about momentum. And that's another important conservational principle from our mechanics. And so Compton focuses on the momentum here and says, okay, this electron, again, not only got kinetic energy, so that photon must have kinetic energy, but it got momentum, and so that photon must have momentum. That's the brilliance here. That's the next step. It's for Compton to say that these photons not just have energy, they also have momentum. That's how that electron got it. Now hang on for a second. I bumped this a moment ago, and I'm worried about the sound. So I'm going to circle around here to the camera, and I do this a lot, and I don't have a chance for Ron to say, hey, do a sound check. Hello? Okay. And so I'll just put the earpiece up to my ear, and it seems to be working, and so the view of it, in fact, is, well, head back as long as I'm over here. Just kind of check if I'm still kind of, getting everything on the screen. It seems to be pointed well. I haven't moved anything. All right. So let me come back into the picture here and just say, all right, here is our next step in our discussion. So our next step here in this discussion is about momentum. All right, let me pull this up and turn down the screen. And again, take a look at Compton's thinking. And I will begin with a very important equation that we finished. Now, where'd it go? We finished the last chapter on. And the reason I emphasized it at the end of the last lecture is because I wanted it now. This was Compton's thinking. Compton is saying, how do we really view these little particles that we are now calling photons? Because if the photons are the light and they're going to the speed of light, they can't have any mass. And that's what we were saying at the end. If they don't have any mass, do you really call them particles? And so what do you refer to as a particle? I mean, most people, when you say I have particles like grains of sand, you say, well, you have grains of sand because they have mass. Or if you throw them, you say, well, now they're moving, and so this grain of sand, it has not only mass, but it also has energy, kinetic energy, and it also has momentum. And they would all go together. If you had zero mass, you would have no kinetic energy and no momentum, at least in a classical sense. And I was saying, if you look at this, you find something very interesting. It is quite possible to then say, what if the mass is zero? So in other words, if you are talking about things going close to the speed of light, or in this case, actually going to the speed of light, they could only go the speed of light if they didn't have any mass, because if they had any mass, it takes an infinite amount of energy to go there. So in the last chapter, we said you can't have anything with mass going the speed of light. You can only get closer and closer. So light must not have any mass, because it does actually go the speed of light. It doesn't just go close to the speed of light, it goes the speed of light. And the only way that can work, according to our understanding of our science, is if they have no mass. So if you're going to take all the stuff we've been talking about, Einstein, and say that they are made out of particles called photons, And you're going to say they go the speed of light. That's only possible if they have no mass. And so if you're going to call them particles, they're going to be different particles than we're used to. They're particles with no mass. And Compton is pointing out there, if they have no mass, they can still have energy and momentum. Energy and momentum go together. If they had no energy, they would have no momentum. If they had no momentum, they would have no energy. So those still all couple together. But you can have these weird particles called photons that would only go the speed of light. We have other particles like that. And I don't think we'll get that far this semester, but we could have gluons, another fancy one. Gluons are another one of these weird discovered particles. That might be more of the 60s, 1960, 1963, something like that. But these gluons then go the speed of light. They have no mass, but they do have energy and momentum. And that's what I want you to see here. So if I set m equals to 0, I would say E equals to PC. Maybe to focus my attention on momentum, I would say, here is my new equation. Here is Compton's thinking. Compton's thinking is to take the evidence he's seen and saying, look, little photons have not only energy, because they gave it to the electron, but they must also have momentum with them. And if I take Einstein's earlier work from 1905, I can explain that particles can have energy and momentum. In fact, they must have both, yet still have zero mass. And so this is a new world. All of this of modern physics is a new world. So at the speed of light, you have these things that can have a particle definition, yet they have no mass. We call them particles, though, because they have energy and they have momentum. We like to stay maybe away from the word kinetic energy, but some people argue and say that we should call it kinetic energy because it's the energy of the photon, and the energy is because it's moving. I don't like it because they're just different particles, and I like to just kind of reserve the word kinetic energy for particles of mass, and this energy has nothing to do with its speed anyways, so I like the way your author does it, and most authors do it, they just call it the energy. Well, let me go another step further here, because as we said earlier, starting with Planck and then with Einstein, the energy of this photon is hf. And if we couple that together with the wave nature, you can see that if I write h or f over c from right here, I'll get 1 over the wavelength. And so this becomes h over the wavelength. And so Compton says, let's keep this equation in mind. This equation is saying that we have these little tiny particles that not only have energy, and I'll put that one back here on the board, it's actually this statement, E equals hf, but these little tiny particles also have with them momentum. And that's, like I said, his brilliance of this. He was, okay, they have momentum, and this would be the equation for their momentum. It's why then, if you've ever heard of what we call a solar cell, and hang on here, for some reason your textbook crashed here. I tried to scroll down and it said error and made it restart. And so let me come on down here. See if I can get back into the section I want. Computer says out of memory. Why does it say out of memory? Well, maybe I'll come back to this. I'll just draw a picture of this one, but I think before we done the lecture, I need to come back there anyways. But the picture I was going to show you is some of the proposed future flight and spaceships are to say, let's take the sun, and way out here by Earth, so here's Earth, you put up in space a giant reflecting piece of aluminum. Now, so we don't want it to be real heavy. It'll be a very, very thin sheet of aluminum. But like a sailboat uses the wind and the sail to move through, we would call this a solar sail, because like the wind having momentum that pushes a sailboat through the water, these photons coming from the sun have a momentum. And so what you could do is have these photons come in and bounce off. And then if you maybe put a little capsule here, and so this giant piece of aluminum foil is sitting up there, you're going to get some momentum. Now, I will point out that the momentum of these photons is pretty small. Remember, it's the energy divided by C. And so if you remember just this green light, how low this energy was, right? It was 2.33 electron volts. In terms of energy in joules, that's really small. Then when you divide it by a big number, the speed of light, it's even smaller. That's why oftentimes I think I have a hard time convincing students that these photons carry momentum, because they say, well, look, you shine it on here. And now, if it had enough energy, it might feel warm, and you can convince somebody, hey, it does have energy. But nobody would ever do something like this. You shine it on your arm, and it pushed your arm back. You wouldn't say, whoa, it had momentum. Try that again. Oh, you know, it wouldn't be like hit with a baseball. When you get hit by a baseball, you notice right away it gets pushed back. And that's because the force is related to that transfer of momentum, going way back to physics 110. And so you get hit by a baseball or something smaller, even just a ping pong ball. It hits you, you know it. You feel that slap. You feel that pushback. There's enough momentum transfer that you can actually detect that with your nerve endings. But these photons don't have much, and that's what I'm trying to get at here. They do have some, but not much. And it's so little that when you shine it on somebody's arm, they go, what do you mean it's pushing my arm? Nobody like walks out the door and then gets hit by the sunlight and gets knocked down. You don't go, whoa, sunlight just hit me with all this momentum. It's such a small amount. Like I said, each photon is a small energy, and then you divide it by C, it's even smaller. Now, I will say there's a lot of photons. So you might argue, well, is there enough photons that I feel it? Well, apparently not, because I've walked out the door in the sunlight many times, and I've never felt like the sunlight's pushing me over. So even though it's a lot of photons, the energy and then divided by the speed of light must be so low, I have never felt it. But what I am getting at is if I took a piece of aluminum foil that was made a giant square, and maybe it was 1 mile by 1 mile, then it would hit by a lot of photons, and it would be enough to actually push a small spacecraft. I don't know if it would push one big enough where humans were on it, but maybe one that had some kind of sensors and detectors, and so instead of using rocket fuel to push it to the other planets or even out of the solar system, I could use the solar wind and the solar radiation to kind of push it along here. And that's what I was trying to say. And was trying to call up your picture here. And in fact, maybe I should see what happened to my memory here. And let me just save this so I don't lose it and close a couple of things. And and see what it says now. If I reload it, maybe that's the problem. I got two textbooks open because I wanted to show you something here. I'm going to close one textbook and we'll come back to it. And, oh good, I think it, try my luck here, I'll turn on the display here. But I'm in the right chapter finally. And I think we were just getting past Compton here. So here's Compton, there we go. And it's, this picture, good, it did load. And this is what your author says is, here is this giant, he puts it kind of as a parachute, but the sunlight would be coming in and bouncing off and then pushing this kind of like the wind would push a giant sail, or this looks a little bit more like a parachute here. All right, well, finally we get to the last part, and I'll even say the best part of this chapter, because everything we've been talking about so far is really building up to the fourth player that you'll see in this chapter, and that is de Broglie. And de Broglie takes this work by Compton, and maybe I will leave the boxed equations up here. And de Broglie has a very, very clever thought. He starts with this idea that, wait a minute, before the introduction here of quantum mechanics by Planck and Einstein and Compton, we thought of light as a wave. And then, through a couple of experiments, we started with the black body radiation, and then we see it also in the photoelectric effect, and we see it in Compton's experiments. We cannot explain the full nature of light without thinking of them also as particles. And so, and Einstein coined this first. Einstein says, yeah, we have to think of it as a duality. And that what he means by that duality is some experiments, and if you remember back to our optics, our wave optics, we did like that double slit experiment and we got the interference pattern. Remember that? Because I'm going to show it to you again. But during that experiment, it only made sense if the light had constructive and destructive interference. So it only made sense we treated them as waves. That's why so many of the early scientists thought of those waves. And Einstein is trying to say that we still got to think of them that way. You still have to think of them as waves. We're not saying get rid of your model of waves, but we are saying you have to complement it with the particle nature. Which begs the question, well, which is it? And Einstein's going to say, look, it's a duality. It's both. Don't be so naive to think that it has to be just one or the other. It's a little bit like, me looking at you as a student and say, okay, I got a question for you. Are you a student or are you an employee? Come on, tell me, are you one or the other? And that's kind of foolish of me. Because why can't you be both? I bet most of you are both. I mean, obviously all of you are students because you're here in class watching this video. But most of you probably have some kind of side job so you can have a little money to pay rent or maybe do something fun with. And so you probably are an employee too. And in some situations, like right now, I would say you look to me like students. But for me to say you're always a student is a mistake. Because maybe on the weekend you have a job, and on that job you're now an employee. Now, I know it's always kind of a weird scenario when I come across, a student in town and, I'm at Trader Joe's and there they are cashing me out and they're like, oh, Oh, yeah, you're a cashier at Trader Joe's. I thought you were a student. See, it would, again, be just a terrible mistake for me to say you're one or the other. The reality is you're both. And that's what I'm trying to get at. This is Einstein's more of his brilliance and his boldness. He says the problem is not that it's both. The problem is we as scientists are trying to make it one or the other. Nature is both. It's why I really like this little picture here. Let me see if it will call up without crashing here. Oh, good. But Einstein is going to coin the phrase duality. And he simply says light is a... And what is it? And if you look closely at this picture, you will see it says both waves and particles. On the big picture, you would see it's a wave. It would go W, A, V, E, then exclamation point. Oh, a wave. Yeah, big picture, light looks like a wave. But on the little picture, the stuff we've been talking about, it's a particle. And if you look closely at the little picture here, you'll see a P, an A, an R, a T, an I, a C, an L, and an E. I like the phrase wavicle. That's what light is. Light is a wavicle. It is both a wave and a particle. It has a duality. And so this is Einstein's explanation. This is what de Broglie is going to run with, the duality. And so let me just emphasize here, because a lot of people struggle with the duality and they want to know, is light a particle or a wave? And I just need you to know from a science perspective, we don't even try to answer that. Trying to say it's one or the other is as foolish as trying to ask a person if they are a student or an employee. The reality is they're both. And whatever they're doing at that moment may indicate to you, in other words, the experiment I run. Right now, if I was running an experiment on you and I was observing you and I was trying to say, are you a student or are you an employee? I would come to the conclusion you're a student. But if I foolishly say you're always a student, that's just poor science on my part. And that's what Einstein's trying to say. There's a duality here. They're both. It's not like it's one or the other. They're both at the same time, and whatever experiment we run seems to show that nature. Sometimes it's a particle, like in the photoelectric effect. But sometimes it's a wave, like we did in the Thomson double slit experiment back in our optics. And so I'm trying to emphasize, do not get rid of your thinking about light being a wave. It's still true. But it's also a particle. It's a wavicle. And so I really like that word, wavicle. That's what light is. Now, like I said, de Broglie comes into this picture with that in mind. And de Broglie must be in the 20s, I think. No, that's Schrodinger. Not sure. Maybe de Broglie's in the teens. But keep in mind then that de Broglie has a little bit of the past history of the development of wavicles of this dual nature in terms of light. And de Broglie has a brilliant idea. He says, whoa, wait a minute. If I understand the development of science, we thought light was a wave. And actually, by the way, even further back, Newton was convinced light were particles. And then it was the double slit experiment that kind of convinced the rest of the world, together with Maxwell's equations, that said, hey, they got to be waves. And so everybody kind of abandoned Newton's thinking. As much as we love Newton, he wasn't perfect, and we abandoned him and say, okay, they must be waves. But then when Einstein comes back into the picture, we're back to particles again, but not throwing away waves. So where we are in our understanding is they're wavicles. They're both at the same time, and trying to make them one or the other is the falsity of it. As humans, trying to put them in a box. It's really just one big box. They're both at the same time. So keeping that in mind, de Broglie has this brilliant idea. He says that if light has this duality, what about electrons? See, let me emphasize. Electrons at that point in history have always been thought of as particles. Nobody ever thought of them as waves. Nobody even kind of questioned that they would be something. There was no experimental evidence leading de Broglie down this road. De Broglie is just asking more of an intellectual question. He's saying, okay, I see what happened with light. Starting off with particles with Newton, kind of ruling that out and making them waves with the Thomson and the double slit and Maxwell. Only to have Einstein and Planck come back and argue, no, the wave doesn't explain the whole thing. They have to also be particles. Not that we're trying to get rid of the waves, because you need the waves to explain the other experiments like the Young's double slit. I want to be careful. I guess that was Young's double slit. Thomson's a different one. So forgive me, earlier on I called it Thomson's double slit. So the Young's double slit and the Maxwell's equation, but now we're going to say they're both at the same time. And so this chapter kind of wraps up with de Broglie going, I got a brilliant idea. I don't know if it's true or not. I just got an idea. That if all of this discussion about the light having a duality, perhaps these things that we call electrons have a duality about them also. Perhaps we have only advanced science enough to say that they are particles. But what if they were also waves? What if they also had a dual nature? And so de Broglie kind of looks over his thinking and says, maybe the momentum of an electron is also equal to Planck's constant divided by its wavelength. Now, again, I want to emphasize, we saw this and we were talking about light or photons only when we were dealing with Compton and Einstein and Planck. But de Broglie is going to come along and say, perhaps nature does this for electrons also. And so I'm going to give you this same equation twice. But I want you to realize there's something very important that is different here. See, this is how we were applying it to photons. Now, de Broglie is going to apply this to electrons. Now, I'll prove to you for a moment that if this is true, then this can't be true. So this equation up here is true for light and light only. It is not true for electrons. In fact, you could do this. You could say that the kinetic energy of an electron is 1/2 mv squared. If you multiply the top by another m, of course, then you have to do the bottom. But I wanted to do that because that would mean then I have an mv squared, which is momentum. So we could say then that the kinetic energy for an electron would also be thought of in terms of its wavelength. But you would have to put momentum squared, which would make an h squared over a wavelength squared. And so notice this does not match that, which kind of makes sense because the electron does not go the speed of light and has mass, but the photon does. So having a different equation for the energy does make sense. In fact, at this point, I would say there's no real justification that the momentum equations match. In fact, I would say there's no justification other than it is a good intellectual discussion that the electron should even have a wavelength. But nonetheless, de Broglie comes along and says, I wonder if nature also has a duality for the electrons. We've advanced our science enough to say there is a duality for the photons, but is there a duality for the electrons? And like I said, de Broglie is the first one to ask it and says yes. And his approach is to say that the equation for the momentum for the electrons, treating them as a wave, is the same as for the light, which would lead to this equation for the energy of the electron. So the equation for the energy is not the same as light. And again, that makes sense because light always goes just the speed of light, where an electron varies. And so it just kind of brings up this natural question, is that even true? By the way, what I love about these equations now is you see the duality in the equation themselves. Did you catch that? Look at this equation. When you say the energy of the photon, you are saying a particle. But you're saying it's related to its frequency. That's a wave. I mean, you have a duality just built in the equation itself. You can't even solve the equation or think about the equation unless you are thinking of it as a wavicle, unless you are thinking of it as both a particle and a wave at the same time. And you see that in every equation. Look at this. Momentum, that is a particle quantity. But you can't really talk about or calculate its momentum unless you know its wavelength, and that's a wave property. And so you are setting a wave property equal to a particle property. That is the duality. And not only do you see it here for the photons, but you see it also here for the electrons. Of course, it's the same equation for the electrons as the photons, but you see it here for the kinetic energy. I would say kinetic energy is a particle aspect, but I can't calculate the kinetic energy without also saying what is the wavelength. And so this is the wave nature of it. And so I just love those equations because they're just screaming at you. You got to treat it as both. In order to calculate one or the other, to calculate the wavelength, I got to treat it as a particle with energy. Or to calculate its energy, I got to treat it as a wave with a wavelength. And so, like I said, it's just, to me, fascinating and very interesting. All right, well, I better wrap up this chapter. It's getting close to our, we really should take a break, and then we'll do some examples here. But I should point out that even though de Broglie kind of starts his thinking by saying, this is an interesting question, I wonder if it is true, there is experimental evidence of this. At least there is today. And I'll give you kind of the first one here. The first one, your author shows experiment done by Davison was going on at that particular time. And Davison was shooting electrons at nickel. And in Davison's mind, he was saying, look, I have electrons. Those are little tiny particles, like little tiny BBs. And I'm shooting them at nickel. It's actually nickel oxide. Actually, it was discovered by mistake. He was trying to shoot it at nickel. And then nickel oxidizes real easy, so he was trying to keep it away from the air. And so he kept it in a little chamber, a vacuum chamber, but then there was a break, and so the oxygen got in and made a layer of oxygen, and so he had nickel oxide. But luckily for him and for the scientific world, that nickel oxide makes layers and spacing between the atoms. And so it kind of behaved as a double slit. And so when Davison shoots the electrons at this nickel, which we thought was nickel, but it turns out to be nickel oxide, and it turns to have these slits in them, he goes, whoa. Look at what I got out. And he looks at the electrons as they bounce off and as they transmit through the nickel. And he sees a fringe pattern. Bright, dark, bright, dark, bright, dark. Like the Young's double slit I was talking about. And like we saw in our optics. And Davidson just goes, what is this? Where did this come from? What does it even mean? And of course, Davidson didn't have any clue what it was. But a third scientist, I forget the name, sees the work by Davidson, and he sees the work done by de Broglie, and puts the two together and says, gentlemen, we have proof now of de Broglie's idea. See, Davidson, you wouldn't get this result. You can't explain this result. It looks like a double slit experiment. It looks like the electrons are behaving as waves, and that's exactly what de Broglie is setting up as his hypothesis. De Broglie is saying that perhaps electrons are waves, and we need to run experiments to prove it, and this Davidson experiment is the first one. And from there, it just blossoms. Maybe I'll show you another one. This is why I was trying to call up the other textbook, so maybe I'll close that so I don't run out of memory here. And I guess I'm done with that one. But in this textbook, which I use for the engineering class, and its introduction to quantum mechanics, they show a fun historical experiment where after the Davidson's experiment, and they show it right here, let me make it a little bigger, they say, well, if this is true, then instead of just using nickel oxide, why don't we actually then build a double slit? Literally take some very thin foil, cut some slits in it, like an aluminum foil, although you can cut it thinner with gold, so we'll do a gold foil, and then let's shine through that, or shoot through that, electrons, and let's see what pattern we get on the other side. And if we get this kind of bright, dark, bright, dark, bright, dark, then what de Broglie is saying is more true. And sure enough, they try it, and they do get these pictures. And here's some pictures of their results on the detector after going through. And so this first one shows what did they get after sending 28 electrons. And at that point, you would say, I don't really know what's happening. With only one electron, you certainly wouldn't see a whole pattern. But then after 1,000 electrons, this is the pattern where they hit. After 10,000 electrons, this is how they hit. And he doesn't give a number here, but after a lot of electrons, you clearly have a constructive and destructive interference pattern. And what's interesting is it seems to be happening one electron at a time and then accumulating, and you don't see the whole result because you don't have enough particles. It would be just like the photons. We talked about this interference pattern where we had trillions and trillions of photons. That's how we get the bright and dark pattern, and that's what this one is showing. This one is showing then that even if you only have a few electrons, the underlying pattern, you might even call it then the probability that the electrons hit at a particular spot, is based upon this interference pattern. And so even just one electron is somehow behaving as a wave and somehow going through both slits and interfering with itself and landing in the appropriate spot, because they did this one electron at a time. It's not like they had a bunch of electrons go through one slit and a bunch go through the other and then they interfere. This is one at a time. And this is what makes duality kind of a hard thing to digest for the beginning student. They're like, whoa, 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 you mean the electron kind of separated? Well, yeah, I mean, if this was light, you wouldn't say it's hooked together. Now, particle you would, but we got to do both. Well, we got to say it's both at the same time. And so it's kind of, it goes through the slit, it's kind of oozing around, it's kind of a wave, it goes through both at the same time. And then yet it kind of interferes with itself and then becomes one solid object. Now it becomes a particle when it hits our detector. And that's kind of a hard piece to digest. In fact, that's a whole lecture in itself, and so I'll stop shy of that. But I did want to show you that there is this experiment, and that's not the only one, not even close. In fact, to maybe wrap up this lecture here, why don't I just show you two more things. The first one, it's actually a nice little picture this author has. I was going to say right here at the beginning. Bummer. It didn't load. But, you know, I have one on my desktop. Let me do this one. See, with today's technology, we can begin to see things on a really small scale. And so within the last decade, this image was taken. And to understand it, these little spikes are actually little pieces of iron atoms. And so with today's technology, you could actually take a substrate. I think the substrate is a nickel, but I'm not real sure. They took a nickel and they took individual iron atoms and they placed them in a ring, one atom at a time, and made a circle. And I guess we could count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'll call it 12 times 4. Okay, so there's probably 48, maybe 50 atoms making what we're going to call a corral. And we make this little circle. And here's the brilliance of it. Then they took an electron and they drop it in the corral. Now, let me change your thinking. If this was a beaker of water and you dropped a water droplet in the beaker, you would see this ripple effect. You would see the waves that are confined by the beaker, and they would look like this. And this is the experiment they're trying to do. Can you see the actual wave nature of an electron? And amazingly, they can. Granted, this is 100 years from Broglie, but it's amazing what we can now see 100 years later. We can actually see a wave pattern when you drop that one electron in the corral. And that is more than evidence that you got to think about electrons, not just photons, but also electrons as a duality. Well, the other picture I want to show you, especially because you guys are in the life sciences here, and so coming back to this chapter before we left, is this might, I think, and hopefully will help you understand the electron microscope. Oh, bummer. It looks like I'm still having troubles. Ah, there it goes. I just made it a little bigger and it draws it. But most of you have probably heard the idea of an electron microscope. How is that different than an optical microscope? Well, with an optical microscope, what you do is you take your small little sample. Maybe you're looking at some little dust mite, and that's what is actually in here, a little tiny dust mite. And you put this dust mite under the microscope, and you shine a bright light on it, and then you have some optics that come down. And just like we talked about in the last chapters about a microscope and how you have an objective piece and an eyepiece and how the two work together to amplify and make it look bigger. And you can look at this and say, okay, now this little tiny thing that was hard to see now gets magnified, and I can see this dust mite. But what we also said is the light has to scatter off, and so because of that you got to get interference, and because of that you could not see details smaller than the wavelength of the light. So an optical microscope is great, except it is limited in the sense that you cannot see things closer than one wavelength. Now remember, visible light, I'll just pick the middle of the spectrum, is about 550 nanometers. So the best you're ever going to see with an optical microscope is things that are as close as 500 nanometers. Now that's pretty good. And so optical microscopes are great, but they got their limits. Now you might say, well, go to a different wavelength, go to violet. Okay, fine, but now remember, they're going to have more energy per photon. You might say go to X-rays. Okay, but again, now you got a whole new world. You're not going to be able to see that with your eyes. We're still, X-rays, the amount of energy per one photon, as we started at the beginning of this lecture, is enormous. We will destroy whatever we're looking at. And if it wasn't dead already, it would be. But even then, it might just kind of evaporate because we blasted it with these X-rays. So what do? Well, you can't keep looking at it with visible light. Is there something we could shine on it that would behave like a wave and have interference, but yet doesn't have as much energy? And that's what these electrons are doing. I didn't run through this equation, but for a small amount of energy, you can get a small wavelength. And so, knowing that, scientists many decades ago developed the electron microscope. They said, look, here is the answer to how we can see things even smaller than we can with an optical microscope. We're at the limit of our technology and our ability with an optical one. Let's switch to a different type of wave. And let's get an interference from electrons. Now, of course, to see it with your eyes, those electrons have to go through some electronics and be displayed on a screen, but at least you don't destroy the sample you're looking at, and you can still then look at it. And so that's what all this crazy stuff is. It is shooting electrons that have a really small wavelength, but they don't have, and I want to emphasize this, they don't have a lot of energy. That's what this math is saying. So we won't destroy the dust mite, even if it's already dead. At least we can look at it in its dead state. We won't destroy it, blow it up, and we can see that. And of course, this photograph is actually then showing what a real one might look like, and then of course the optical electrons get converted in this part and converted into a visual picture on a screen that somebody can look at it. And most electron microscopes these days don't even have you kind of looking in here. They just have a big monitor on the side. Why look in there? You just put the sample in there and you look on the screen here. But you're not just amplifying the light, is what I'm trying to get at. And you are using the wave nature of the electron. You're using this de Broglie, and that's the other thing I want to get to. So here is then a photograph of this dust mite. And I wonder if I made it a little bigger, if you could even see the details. Oh, you know what? I bet the PDF. Yeah. So sadly, the PDF has a limited resolution, so that doesn't look very, very good. But the real photograph of this would have really good details. And so these little hairs coming off the dust mite actually have hairs off of the hairs. And I'm sure there's some fancy name you guys in the life science call those, but that's amazing of how much detail you can pick out. All right, well, like I said, it's time for a break, but one last thing, because this is what I call the grand finale of de Broglie's thinking. I will take you back. I believe it goes all the way back to chapter 17 in physics 120 or 110 here. So way back, we did this. We took a string and we tied it to this post. You might even remember me doing this. And I used this as an opportunity to talk about standing waves. Standing waves on a string. Now mine's not really a string here. Mine is a spring, but it's the same basic idea. And again, just to kind of recap your memory from back then, I did something like this. I said, if we take this string or spring and we tie it on both ends, so this end I'm going to hold it with my hand and the other end I got clamped, and I let this thing shake, one possibility is from one end to the other, which we call node to node, would be one hump. That's a half wavelength. But there are other possibilities. We could have a pattern that looked like this, if you remember. And so there's a node in the middle. So besides having the node at each end, there's one in the middle, and so we'd have two humps. And so you might say the distance between these is one wavelength. Now, there's another possibility. There is the possibility, see if I can set up the pattern, there we go, that we have three humps. So there's two nodes in the middle, then the one's on the end. So I guess I call it four nodes, but there's three humps, and each is a half wavelength. So this length represents a wavelength and a half. Ah. Did you just see how I was saying that the wavelength has to be a certain quantized pattern? It's just part of the wave nature. And if electrons are actually waves, and these waves are trapped in the atom, then you have to have an integer number of wavelengths in this atom, and so the wavelength has to be quantized, which means the frequency has to be quantized, which means the energy has to be quantized. And that's the grand finale. Why do we even have quantum mechanics? See, remember when I started this? Remember I started this whole lecture and I said Planck says, look, if it's quantized, it explains the black body radiation. He doesn't believe it. It just doesn't feel right for him. He has no way to explain it. He's not bold enough to just say it is what it is and move on. It'll take Einstein with the photoelectric effect to come along and say, look, it is quantized. Accept it. That's what the experiments say. If it bothers you, so be it. I don't care if it bothers you. This is just what the science says. But Einstein doesn't give us an explanation of why it is quantized. Finally, at the end of this chapter, I can give you what was missing for Planck at the very beginning. Planck is bothered by this quantum nature because he is thinking of the electrons as particles, not as waves. It will take a number of decades, at least 2, maybe 3, before de Broglie says, I've got an answer for you, Planck. I got what was bothering you. Einstein, I got an answer for you of why the world is quantized. Einstein, like I said, was at least bold enough to say it is. I don't understand why, but it is. I accept it. But de Broglie is the one who takes this from light to electrons and then says, if you think of the electrons as a wave, just like we did for the guitar string when we did our acoustics, and I'll show you again, where it has to be quantized. Well, maybe I'll start with that one. So it has to be either that or this. Or, and I'll stop now because I've been talking too much, but I want you to see what de Broglie is saying here is just the quantum nature itself is evidence that electrons are waves. I'll say it again, Planck didn't know that. Planck didn't understand that. Planck just said, what if the atom was quantized? And he gave a pattern, and he said that pattern for the atom being quantized would then lead to the light being quantized. Einstein took it further to say we just accept it. But it's here with de Broglie. And the same work we did for our acoustics, if we apply that to the atom and we say the electron in the atom is a wave, and it's this wave pattern that then is the energy, then the energy has to be quantized. For you who already took chemistry, I'm not sure if that comes across in a beginning chemistry class well enough. Do you remember those s orbitals you looked at, and those p orbitals, and those d orbitals, and those f orbitals, and all those cloud drawings with dots? I mean, what were those pictures trying to say? Those were pictures which were trying to show you the wave pattern. They were trying to say the electron is not a particle, and it has just a point to it. It is a wave. And as the wave goes around the atom, you have to have an integer number of wavelengths to come back, otherwise you would get destructive interference. And so it is now quantized. And that finally finishes up this lecture of that's why there's quantum mechanics, because electrons are a wavicle. Sometimes I got to think of them as particles, but sometimes I think of them as a wave. And when I think of them as a wave, not only can I use it for an electron microscope, but I understand now why things are quantized. All right, let's take our 15-minute break, and we'll come back, and then we will then do some examples, because I think doing some example calculations will be helpful for you. All right, everybody. Hey, welcome back. We had a nice 15-minute break. Same idea. I know I'm not in the camera screen right now. Let me circle around to the front of the room. Hello. I'm just starting the camera and checking the sound, and looks like it's good to go. Let's take all these words, and I know it was kind of a big story time about the history and the meaning behind them, and hopefully it wasn't too wordy, but let's put this now into practice. Let's see if we could do some of these problems and take these ideas and try to remember what they mean and do our calculations here. So I'm going to start here with, say, number 1 here, and I'll go ahead and see how this works. I'll kind of put the question here on the screen, and then maybe move around a little bit, and we'll have to go back and forth since I don't, have a camera person here, but let's try this one. This one says number 1, and so I'll put here, all right, let's try number 1 here together first. And this goes back to the idea of Planck. This was kind of our first discussion here about the vibration. And it says here, it looks like a lithium bromide molecule oscillates with a frequency of, and they give the number. It says, what is the difference in energy in electron volts between the allowed energy states? What is the approximate value of N for the state having an energy of about 1 electron volt? Okay, so let me go ahead and mute the question there, and I've got my hard copy of my book here so I can refer back to it. But A says, what is the difference in energy in electron volts between the allowed states? So if you remember our discussion, we said that the energy of each state was N plus a half times HF. And if you also remember, Planck didn't recognize that 1/2. Planck just recognized that the energy between each state would be HF. And therefore he assumed that the atoms just had an integer of these, so there's the integer, but he didn't realize the 1/2. But I think this problem probably wants us to use the 1/2. In fact, for A, this doesn't even come into play. This just says the energy between each state. So let's say we are at state number 7, kind of like the steps going up the side of the building. So we're at 7, and then we're asked to go to the next one, 8. And so the difference between a 7 and an 8 is just HF. All right, and that's the first one. Let me just kind of double check that again. It says, what is the difference in energy level, and in energy in EVs between allowed states? So let me just take this H, which is this 6.63 times 10 to the negative 34 joules per, or joules times second. You might remember us using that when we calculated the energy of the photons in our laser pointer here. And then times this frequency. If I remember right, it was 1.7 and times 10 to the 13, 13 hertz. And so when I multiply them out, a hertz and a second cancel off, and that means I will get energy in joules. And they asked it for an electron volt, so we'll have to do a unit conversion here. But I'll go 6.63 times 10 to the negative 34, and then I will multiply it by 1.7 times 10 to the 13, and I will get 1.13 times 10 to the negative 20 joules. And then recognizing the conversion factor from a joule to electron volt, so going way back to chapter 1. I'll put joule on the bottom so it'll cancel, and then electron volts. And of course you can only justify this if you're multiplying by a 1. That means what's in the top has to equal what's in the bottom. And sure enough, 1 electron volt is equal to 1.602 times 10 to the minus 19 joules. So, using my calculator, I will then divide that number by 1.602 times 10 to the negative 19, and I get 0.0704 electron volts. And so, not much energy between each layer, each vibration, and so this vibrating what is a dye molecule? What do they call it when there are two atoms? Anyway, so we got two atoms, it's like lithium and a bromide, and they're hooked together and they're vibrating, and they can be at different energy levels, but they have to be quantized. That was the whole point. And so this is the energy between every level. Now, it's not much energy, so for many experiments, if you will, or many of our chemistry, or many of our material science, you might not even need to think about these little tiny steps. You can just think of it as a continuum. And that's what I was saying about the quantum level. Little tiny steps going up the side of the building for something big like me might think, oh, it's just a ramp, I can do any energy levels I want. And in fact, here's what they're saying. If this vibrating molecule actually has an energy, and this is B, what approximately is the value of N if the state has an energy of 1 electron volt? So, in other words, if this energy here is 1 electron volt, then this N value, as we're seeing, is going to have to be a pretty big number to be multiplied by this small number, the HF, between each step. So this is the 0.0704 electron volts. We could then solve this for N. Now, which, by the way, you'll see that the N is so big that the 1/2 is, again, something like Planck would never notice there by the experiments, that there's an extra 1/2. It was amazing you could just find that they had to be quantized. There had to be steps to them. So I'm going to go 1 divided by my last answer. And so I'll move this over here. And so I thought it would be higher than that, but it's only about 14. Although maybe to be a little more accurate, I should subtract the 1/2. And of course, it comes out to be 13.7, although let me not stop there, because I do know that the N is supposed to be an integer. So this is saying that it is either, if I rounded up too high, it would be on the 13th quantum level. If I rounded too low, then maybe it's actually at the 14th level. Since this is kind of close to a 14, I'm going to say it's at the 14th level. And so if I was doing an energy diagram, so energy, the atom could have been as low as this energy, or this, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I'll just draw a little dot there to say this is actually the energy level it's at. It's like going up 14 steps. It's 14 steps up the staircase. It could go higher or could come down. And if it came down 1 step, it would release a photon of this much energy. And this would be way into the, I was going to say infrared, but it would be far infrared. I think it would even be radio waves. And so it would be very low amount of energy. But it would be there. Okay? All right, well, that was a good one. Let's move on to another one. That was kind of where we got started with Planck. And so for a second example, and I think still in that same kind of area, I wrote down moving on to photoelectric effect, number 4 here. All right, so let's read number 4 here together and scroll down. And 4 says this. It says, what is the longest wavelength of electromagnetic radiation that an ejection that can eject a photoelectron from silver. Given that the binding energy for silver, or the work function for silver, is 4.73 electron volts. And of course, is this in the visible range? All right, so kind of reminding you of the lecture on the photoelectric effect, we have this material, and it looks like in this case we're going to be working with silver. So I've got silver, and I've got this wave coming in, and maybe I shouldn't do a little squiggle because that means I'm kind of thinking of it as a wave. I'm going to put here, I'm going to think of it as a photon. And so a photon comes in, and what we said is the photon has an energy of HF. That was Planck's hypothesis. And then Einstein is going to say, yes, that makes a whole lot of sense. And all of that energy goes where? And so when it hits this electron, it will first give some of its energy to breaking the bonds. Okay? Then it will have energy left over, perhaps. So again, if it was too low of a frequency, it wouldn't even break the bond, and so it would be below what we call the cutoff frequency. But if it had a high enough frequency, it would break the bond, break it free, and then there'd be some energy left over to give it some motion. And so depending on how much the frequency is above the cutoff frequency, this could have a little or a lot of kinetic energy once it breaks it free. And so this one says, what is the longest wavelength? So in other words, as the wavelength gets longer and longer, in other words, bigger and bigger, the frequency goes down and down, and so that would be the cutoff frequency. So this is a way of saying, let's set the kinetic energy equal to 0. See, anything that would give it some kinetic energy must have meant the photon had not only enough energy to break the bond, but then had some left over. And so that means the wavelength could have been a little longer, or the frequency a little lower. And this problem is talking about wavelength, even though the equation is in frequency. So I'll say it again. What is the longest wavelength? See, because if we get too long, that's too low of a frequency. We're below the cutoff, and it wouldn't free it up. So what is the longest wavelength that can eject a photoelectron from silver, given that it's binding energy? And did you notice it was in electron volts? And did you notice they're asking about wavelength? Here's why I say that. I want to take a very useful approach for you that you'll find very convenient. Take HF and rewrite it. Rewrite frequency, and I'll put it here, speed of light is frequency times wavelength. Rewrite frequency as speed of light divided by wavelength. Because these two numbers in the top are constant numbers that if we just multiply them together, we can have a constant and we never have to multiply them together again. And so let's take the 6.63 times 10 to the minus 34 joule times a second. Let's take the speed of light, 3 times 10 to the 8th meters per second. And if we multiply those together, oh, well, what do we get? Okay, so 6.63 times 10 to the negative 34 times 3 times 10 to the 8th. And we get a number that is 1.989 times 10 to the negative 25. And the units here would be joules times a meter. Now, part of me wants to stop here and say, okay, this would be nice if I memorized this, because I would never have to then work this out again, because this shows up a lot, and we talk about the photons and wavelength a lot. So this might be worth memorizing, but I'll even do you one better. We often talk about energy in terms of electron volts, and we often talk about the wavelength in nanometers. So let's do a unit conversion from joules to electron volts. Let's also do a unit conversion from meters to nanometers. That way, what I can have is something that says E equals And I'll have up here in the numerator some number that's probably worth memorizing because it would be in EVs for energy, and the wavelength, or the unit up here, would be nanometers, so I could put in my wavelength in nanometers, get nanometers to cancel off, and get energy in electron volts. So this is a nice little convenient trick that'll make your calculations much easier than using all this times 10 to the minus 34 and all these other units. So I wanted to show you that and convince you how much easier this is going to be. But again, you have to memorize another number here. Okay, so let's see. My unit conversion would be 1.602 times 10 to the minus 19 joules is 1 electron volt. And then over here, I guess 1 meter, or maybe I'll put it the other way around, 1 nanometer is 1 billionth of a meter. How about that? That's what nano means. So the number on top and the number on the bottom are the same. Number on top, number on the bottom is the same. But what's going to happen is joules are going to get converted into electron volts. Good. And meter is going to get converted into nanometers. And so I'll say it again, this number would be nice because it would be then wavelength, which I can put in nanometers, would cancel, and I would get energy in terms of electron volts. And that will be very helpful in this problem and other problems. So taking my number that's already in my calculator and dividing it by 1.602 times 10 to the negative 19, and then dividing that by, and we'll just call it 1 times 10 to the negative 9, I get a number that is 1,240. That's about a 42, but we tend to memorize it as just 40. So I'm going to put that on the board. So to 3 significant figures, this is just 1240. And 1240 just seems to be an easy one to remember for some reason, or maybe I've just seen it so much. And so what this is saying is if you take the number 1240 and divide by the wavelength in nanometers, you will get the energy of the photon in electron volts. And that's pretty convenient here. Because using that information up here, let me again replace this with hc over lambda and basically say, when does it equal the binding energy? What wavelength would equal the binding energy? Because as we said, we're going to set the kinetic energy equal to 0 to figure out what is this longest wavelength. That means any wavelength shorter, which of course means any frequency higher, would be enough energy to not only break the bonds, but to make the electrons move a little bit. Okay? But that's going to be my equation. And I'm going to take advantage of this. So right here, I'm going to put the 1240 electron volts times the nanometer. And I'll divide it by a wavelength. And that has to equal to the binding energy, which they gave us. I didn't put it on the board here, but we'll come back here and it says 4.73. So this is 4.73 electron volts. See, that's why I wanted to use this in electron volts, because they gave this to an electron volt. So in other words, instead of converting my electron volts to joules, I will just do that by remembering this number right here. And of course, then I will then see the electron volts cancel off, and I will then be able to give you an answer in nanometers. And so this is going to be my wavelength in nanometers. So let me take my 1240 and divide it by 4.73, and this would be 262 nanometers. And so again, that's the longest. Anything shorter than that, we'll eject it. Which of course is kind of interesting because remember the visible range was 400 nanometers up to 700 nanometers. This is quite a bit smaller than the visible range. There's no visible light has enough energy in its photons to make electrons kick out of silver. So silver may have a photoelectric effect, they all do, but you're not going to see it by holding a piece of silver in your hand. You're not going to have like jewelry made out of silver that, because you're in the sunlight, is going to have electrons being ejected from it because of the sunlight. It's not enough energy. And that's kind of what it's getting at. And that's the second part of this. Is this in the visible range? And no, it's not. All right, well, let's try another one here. Next one on my list is still kind of a photoelectric effect. It's number 14 here. Let me scroll down here. And it's talking about this photoelectric effect again. It says, what is the maximum velocity of the electrons ejected by a material by 80 nanometers photons if they are bound to the material by this 4.73. So it sounds like we're still using silver because that's how much energy it was in the last problem it took to eject them from the silver. And then notice we are at a number of 80, which is much less than the 262 that we just calculated. So it's going to eject them, and then the extra energy is going to be kinetic energy, and that's it. We want to figure out its velocity from all that. So that's the strategy we're heading down here. Let me go ahead and erase most of this, but I maybe will leave this here because we're still working with this photoelectric effect. And so before I erase the last answer, there's that 262 I was just mentioning that, hey, this is much less than that. And I'll leave this handy so that I could actually then maybe just do this. Maybe I'll just take this and put it right in here. So this is saying 1,240 electron volts times nanometers over the wavelength, and in this case is 80 nanometers, must equal then to the binding energy, 4.73 electron volts, and then anything after that is kinetic energy. And maybe I'll do this in 2 steps for your benefit, but if I take this 1240 and divide it by 80, I get 15.5 nanometers cancels off, and I have electron volts. And of course, the nice thing of using this little formula was to get the nanos to cancel off, but then also to have it in units of electron volts so I can subtract off the binding energy. And so the energy left over after we've broken free the electrons is this 15.5 minus 4.73. And so that looks like a 10.8 electron volts. Now, our question is a little further than that. I think they asked for a speed. Let me just come back and check. Yeah, what is the speed of these ejected electrons? And they say the maximum speed because this is what's left over. And you might actually get things that rub and hit as they come off with other stuff. So you might actually get one slower than this. But the energy goes somewhere. But if they don't have any of that, this is the most they could ever have because this is your limited amount of energy you come in with, and you have to give this much to break it free from the silver. So this is the most you could have as kinetic energy if it didn't, bump and rub other things here. So they call it, what is its maximum. Now, I would say at this point, probably it's best now to switch electron volts back to joules, assuming I want to get a speed in meters per second. And I think I do. And so that's meters per second, and then mass in kilograms, that's all connected to a joule. So I'm going to go ahead and then put 10.8 electron volts, and then convert electron volts to a joule. So then when I go 1/2 mv squared, and I put my mass in kilograms, my velocity will be in meters per second because that's what's buried in a joule. So for 1.602 times 10 to the negative 19 joules is in 1 electron volt. And then the mass of these electrons, 9.11 times 10 to the negative 31, is the mass of an electron. And so again, using our principle of conservation of energy way back from physics 110, together with the Planck's hypothesis here, we can figure out how much kinetic energy, which I guess we already did, and then figure out how fast it's going. All right, so here I've got my 10.77 in my calculator. Well, let me multiply it by 1.602 times 10 to the negative 19. So that's the amount of energy, which is 1.73 times 10 to the minus 8. Let me bring this 2 over, so times 2. Let me then divide by the mass, 9.11 times 10 to the negative 31. I'll just hit enter. So that would be the speed squared. And so last step would be to say, let's take the square root. And so I would get a speed v of, looks like 1.94 times 10 to the 1, 2, 3, 4, 5, 6. And then notice, by the way, that's a big number. It didn't seem like it would be that big. The energy was so small. But remember, these are little tiny electrons. They got very little mass. So even a little bit of energy means they go very, very fast. And so sure, it's going almost 2 million meters a second, which again sounds very fast, but remember that's still way under our 10% the speed of light. 10% the speed of light would be 3 times 10 to the 7th. And also, had they been going that fast, I better not use 1/2 mv squared for the kinetic energy. I better use gamma minus 1 mc squared from the last chapter if we were exceeding 10% the speed of light. So these little electrons, it's easy to accidentally give them so much energy that they go greater than 10% the speed of light. But for our discussion, as I said at the beginning of the lecture, that little diagram, I said we are going to look at things that are small but go slow compared to the speed of light. And that's just confirming it that, yeah, this is still quite a bit under 10% the speed of light. It's not even 1%. 3 times 10 to the 6 would be 1%. So it's 2/3 of that. So it's 2/3 of 1%. So quite a bit smaller. All right, well, that was a good 2 problems on photoelectric effect. Let's move over to Compton here and Compton's experiment and his thinking about these electrons not just having energy but also having momentum. I believe it's number 23 I put first on my list here, so let's give that one a shot here. And so 23 says, what is the wavelength of a 1 electron volt photon? B, find its frequency in hertz, and C, identify where it is on the electromagnetic spectrum. Well, this isn't too much of a Compton problem yet. It's starting there. But this is really this electromagnetic spectrum. And so maybe I spoke a little early. These next 2 are about the electromagnetic spectrum, not the Compton effect here. All right, so clearing off the board here so I can have some room to work. Let me start off by saying again that the energy, you can think of it as HF, but also very convenient is HC over lambda, where HC is that 1240 electron volts times nanometers if you want to work in energies of electron volts and nanometers. And we do a lot because wavelengths are so small, it's nice to work with nanometers. And energies are so small, it's nice to work with electron volts. And then 1240 is kind of easy to remember. Now, I think this said a photon of 1 electron volts. Let's see. What is the wavelength of a 1 electron photon? So I'm going to then set the energy equal to 1 electron volt. And then I'll put in my 1240. And then, of course, you'll see that electron volts, it's nice, it cancels off. And then you can just move the wavelength over and you get 1,240 nanometers. And I'll just remind you, the visible spectrum was the 400 to 700 nanometers. So this is bigger, and so I'd say it's past the red. It's the infrared here. And that might have been the next part of the question. It says, identify what it is in the chart. Yeah, I'm gonna, so I don't mess up all the page numbers here. Maybe I'll flip over here in the chart. But I'm very convinced that this 1,000 nanometers would be in the infrared. Oh, they listed it as in frequency. Yeah, but anyways, definitely infrared. In fact, didn't they say here, maybe I skipped to part B. Yeah, part B said find its frequency also. Okay, so I got its wavelength. Let me also find its frequency. And so frequency is the speed of light divided by its wavelength. So 3 times 10 to the 8th meters per second. And the wavelength, as we just said, is 1,240. And I'll now put in nano as 10 to the minus 9 meters. So that meters will cancel off, and I'll just be left with 1 over seconds, which is a hertz. And so grabbing my calculator here, I can say, all right, let's take 3 times 10 to the 8th, and let's divide it by 1,240 times 10 to the minus 9. And I get 2.4 times 10 to the 14. Maybe I'll write that as 240 times 10 to the 12. Or maybe I will write that as 240 terahertz. So these frequencies are really high, even when they're in the infrared, and you're thinking, oh, that's low frequency. Our definition of low frequency is hundreds of terahertz. And so these frequencies are really high. And again, looking at this spectrum, here's the 10 to the 14th, and yeah, infrared is a big band in there, and so it's inside the infrared, but really not near the edge. It's kind of it's not really kind of the middle either. It's kind of over, looks like on this chart, towards the higher frequency of the middle. So high of middle, but it's definitely infrared. All right, well, that was what, 23. The next one I put on here was 28. I thought 28 would be a good one to do. And so let's look here at number 28. Let's see if it's on the screen. Okay, well, barely on the screen. Maybe I'll scroll up a little bit here. But 28 says, what is the maximum energy in electron volts of photons that are produced in a CRT, that's called a cathode ray tube, using 25 kilovolts, that's 25,000 volts, accelerating potential, such as very common in, I'll call it an old school color television, one that used one of those big CRT tubes. And what is their frequency? Now, this one, if it's not obvious, is going to be a lot of energy. And so let's talk about the acceleration of an electron. We mentioned this way back when we started this semester about electrons and giving them energy and how do we do that, and then the principle of conservation of energy. And so maybe it's worth reviewing here, but if you had a wire that had some resistance on it, and so you put a power supply to it, you're going to send current through here, and this is going to get very hot. And when it gets hot, of course, like a light bulb, it gives off the visible light. That's what I was showing at the beginning of this lecture. I got this filament really hot, and as the atoms bounced around, they would give off light. But also when they are bouncing around, and I didn't mention this, they would kick off a few electrons. Now that by themselves is probably not going very fast, but if nearby you put a plate that is charged positively, these ejected electrons, and I shouldn't call them ejected because they just kind of knock off. So we call them boiled electrons. It's kind of the analogy of boiling water. They hit together and some water molecules up at the top break free and meander away. That's a pot of boiling water. And that's kind of our picture here is we've got boiling electrons. So we take these boiling electrons, but then we give them a really big speed because once they break free from say their tungsten inside, then we really give them a large speed by accelerating them. Most of them will just hit the positive plate. But this positive plate has a small hole in it. And some of them, a very small number of them, actually just happen to be kind of balanced between the top and the bottom, and they go actually right through the little hole. And so kind of like a little porous hole in the metal. And then they don't hit, but they come out the other side. So we refer to this as an electron gun. So we first boil them, then we accelerate them, then they come shooting out. And of course, how much kinetic energy do they have is gained from how much electrical potential energy, which we learned was their charge times their voltage going back to the beginning of this semester. I think that was the second or third chapter we did this semester. And so what I can say is the kinetic energy is Q times the voltage. So that's how much kinetic energy they have. Now this problem goes one step further. This is talking about a cathode ray tube, and so this is kind of the building of a cathode ray tube. We first boil off the electrons, then we accelerate them with an accelerating voltage, so we turn electrical energy into kinetic energy. But then we have a screen, and the electrons hit and give off lights, and so we'll shoot them into different materials. And some materials give off green light, and some give off blue. What is it? RGB, so red, green, and blue. And so we put different pigments in there so that when they get hit by these electrons, they'll give off different colors. And so you can then formate on the screen, light coming from your screen is either a red, green, or a blue. And of course, they're little tiny dots, and you put a bunch of them together. You get different combinations of intensities of red and green and blue, and that's how the TV works. And so that's why you talk about like a high definition TV, what do you call it, 1080. That means that these little dots, there's 1,080 of them this way, and there's something like 19 something, almost 2,000 dots this way. So 2,000 this way and a little over 1,000 that way. That's like 2 million little tiny dots, and each dot has 3 dots, a red, green, and a blue. And so the TV technology is amazing in terms of the engineering, but each of them are getting hit by this electron. At least the old school ones were getting hit by electrons. Now the newer ones have LCD lighting. But as they get hit, they're going to give off the light. And that's what this problem is getting at. It says, what is the maximum energy in electron volts of the photon that's produced in a cathode ray tube using an acceleration of 25,000 volts? And so I would argue that the most energy that this photon can have is also equal to the most kinetic energy the electron can have, and the most it can have is then equal to this accelerating voltage. So if I say that this is the charge E of the electron, and the voltage is 25,000 volts, I can then get 25,000, and then I'll just put the E with the V and say EVs. And so this photon could have 25,000 EVs. Now, it won't have that much. That's huge. Remember, the visible range, we were working with numbers like 2 and 3 and 4 electron volts for the visible range. This is way, way over that. And then, of course, it says, such as the color TV, what is this frequency? So maybe if I use this energy of the photon and set it equal to, hc over lambda, I can write this as 1,240 electron volts times nanometer over its wavelength. And so the electron volts would cancel off, and I would be left with nanometers, and this would be an incredibly small wavelength, 1,240 divided by 25,000. In fact, it's such incredibly small, I'm questioning if I'm doing this right. But it seems right. They say 25,000 volts, and I think the most we could get. The reality is we would not get that. That's not even what we want. We want the color coming out of the screen to be 2 or 3 electron volts. That's the visible range. So a lot of energy can be wasted along the way, and it is. And so that's why they don't have this particular wavelength. Now, I'm not quite done, because this problem said then find the frequency. So let me take the speed of light and divide it by its wavelength, and let me be mindful of the units. And so I'm going to get a frequency in hertz. So 3 times 10 to the 8th divided by 0.0496 times 10 to the negative 9 is some incredibly high frequency. Ridiculously high frequency, way out of the visible range. We're not in those hundreds of terahertz that we're used to seeing for the visible range. Again, that would be the most you're seeing. But there's other things going on. Instead of getting one high energy photon, we would actually like this to give off a bunch of low energy photons. That's how we want to conserve energy. But I think that's what they wanted me to do. All right. Well, I don't know if that was such a good one, but nonetheless, it helped us with some calculation. All right. Well, another one here I put, and I guess this is now finally a little bit about Compton and momentum, is number 42. And so let me pull this down here. Let me turn on here. Let me scroll down to the bottom of this column and read number 42. 42 says, calculate the momentum of a photon having a wavelength of about 2.5 micrometers. So again, infrared. B, find the velocity of electron that would have the same amount of momentum. And then C, what is the kinetic energy of this electron and how does it compare to the photon? And actually what I really like about that C part of the question is, do you remember at the end of the lecture I was talking about why the need and the usefulness of the electron microscope? How to get a small wavelength in order to see something small. If we used photons, it would have a lot of energy and destroy that dust mite we were looking at. But here you're going to see the numbers, and you're going to see we can get a small wavelength and a small energy if we use electrons. So we can actually see details because of the small wavelength of the electrons without destroying what we are looking at, so we can, continue to look at it. We can't look at it if every time we turn on the source, the whole dust mite explodes into little pieces. You just can't study it that way. And so that is the real neat thing about using the property of electrons and their wave property. Remember, they're wavicles too. That's this whole argument about de Broglie and the whole wavelength thing. All right, so let me clear off the board here and give another calculation here. And looks like there was a bunch of parts to it. And let me kind of remind myself what one we're doing. It was number 42. And 42 says, calculate the momentum of a photon having a wavelength of. Now, whether it is a photon or an electron, this equation worked for both. Let me just kind of remind you of that. That was de Broglie's hypothesis. So I will keep in mind that they've asked me to get the momentum here of the photon, but I will also then keep in mind that the equation would be the same for the electron. And they give it in terms of a wavelength. And so they say the wavelength is 2.5 micrometers. So there would be my wavelength. And I will go ahead and put the 6.63 times 10 to the negative 34 joule times a second for my Planck's constant. And I'll get a number in a second, but let's just check out our units here. Remember what a joule is. A joule is a Newton times a meter. And so the meter would cancel off. And now we have the appropriate units. If you remember way back to Physics 110, the units for momentum are a Newton times a second, which is also the same as a kilogram meter per second. And so maybe I'll write it that way, kilogram meter per second. So the units work out right. Let me just calculate its number. So 6.63 times 10 to the negative 34. Divided by 2.5 times 10 to the negative 6 gives me a momentum of about 2.65 times 10 to the negative 28. Which, agree, it's a small number. That was kind of my point that I was saying when somebody walks outside the door and the sunlight hits them, they don't feel like they're knocked over. The momentum is so small. Now, granted, that's only one photon, but even a bunch of them, it's just not enough for you to recognize it. But like I said, if there was a bunch of them, you know, like that giant aluminum foil I was talking about making for a spaceship, a solar cell, maybe it is. All right. But anyways, this is the momentum of it. So there's A. Now, B says a little bit further here. B, find the velocity of an electron that has this same momentum. So let me go ahead and just remind myself that momentum is mv. I guess you might say, isn't it gamma mv? And I would say, well, yes, if you get more than 10% the speed of light. This one, as you'll see, is not that fast. We're not going to do any of them that are that fast. So even though we talked about it in the last chapter, go back to your classical physics and just set it equal to mv. And so if this is 0.65 times 10 to the negative 28 kilogram meters per second. And then over here, I put in the mass in kilograms of the electron. So that's at 9.11 times 10 to the negative 31. I then could answer their question and hopefully see some useful numbers here on how low this speed is, at least low compared to the speed of light. It's a pretty big speed if this was a car, but for an electron, this is pathetically low. And so I'll take that momentum and then divide it by 9.11 times 10 to the negative 31 and get a speed that is lower than the speed of sound. Like I said, fast for a car or a boat or a plane, but slow compared to any other electrons, like the one we saw earlier, which was like 2 million meters per second. And so this, I guess, is our speed. And that's kind of what I'm getting at here. It's amazing then that something that has this momentum, which would be a corresponding wavelength, actually is moving very slow and therefore has very little kinetic energy. And I think that's the next step in here. It says, what is the kinetic energy of this electron and how does it compare with that of the photon? Now, I don't think we calculated the energy of the photon. We just had its wavelength. So that's worth doing. And then also maybe over here for the electron. And maybe I'll do the electron first. So the electron, we said, would have a kinetic energy of 1/2 mv squared. And if we just put in our numbers for the mass of the electron, and now this very low speed, you're going to see that the kinetic energy, and this would be in joules, is pretty small. 1/2 times 9.11 times 10 to the negative 31 times 291 squared equals, and so this is 3.85 times 10 to the negative 6 joules. Maybe I'll just, since it's a small number, do a units conversion to electron volts. And so divide by 1.602 times 10 to the negative 19. And this is only 2.41 times 10 to the minus 7 electron volts. So it's a very, very small amount of energy. Now, here's that electron microscope again. Remember, this is its speed, so this is its momentum. And over here, even though we did a calculation thinking of it as the photon, this momentum would go with this wavelength, whether it was a photon or an electron. And so what I'm trying to say here is this is a small amount of energy for this wavelength. But let's see what the energy is for the photon. This will give me hopefully the point that I am looking at the same wavelength for a photon as for an electron, and they don't come out to be the same energy. And the energy of the photon is an enormous amount compared to the electron. That's why, again, that electron microscope is so incredibly useful, such a brilliant piece of technology that we can actually then see details with the wavelength without having to blast it with so much energy. All right, so let's see how much energy we get for the photon. And this will be example to use my HC over lambda again, because this is this 1240 electron volts in nanometers. And so if I divide it by the wavelength now in nanometers, and they gave it in micrometers, so let me write it as 2,500 nanometers. Right, so I'm making this number bigger by 1,000, which to balance it, I have to make this number smaller by 1,000, and that would be 10 to the minus 9. That is a nano. Okay, so nano would cancel off, and I'll get the energy in electron volts. And so this is the 1240 divided by 2,500. And by itself, it's not much energy. That's not my point. This is only about 1/2 an electron volt, which makes sense because it's not even in the visible. This as we said, is over here in the infrared. So I expect it to be under about 1 eV. Sure. And it is. But what I want you to see is if we were looking at a wavelength and we're comparing a wavelength of a photon and that same wavelength of an electron, notice that the energy of that photon being 1/2 of an electron volt is over 1,000,000 times bigger than the energy of the electron. So again, same wavelength, which means if we use them as microscopes, we can see the same detail. But this one is hitting your sample with 1,000,000 times more energy than the electrons, destroying what you're trying to look at. It's 1,000,000 times. And that's why it makes a good problem here. All right, well, let's keep moving on. And 2 more here. We better wrap it up, and hopefully these would be helpful to all of you, or at least one of you, as you kind of look here at this video lecture. And number 50 is the next here on my list. And so number 50 says what? So number 50 says, what is the wavelength of an electron that is moving at 3% the speed of light? Okay, well, I guess I would say this is a lot like I just did on this problem, where I need to kind of remind myself, am I looking at an electron or am I looking at a photon? And you notice I've said that many times purposely because I know that on tests, this is what students mess up on. They go to do a calculation and they do the inappropriate calculation. They do a calculation for a photon instead of an electron, or an electron instead of a photon. And it's easy to do. And I want to just keep emphasizing they have the same equation when you're talking about their momentum, but a different one when you're talking about its energy. All right, I guess I need to read this again. So what is the wavelength of an electron that is moving at 3% the speed of light? So by telling me I'm moving at 3% the speed of light, they are telling me its speed, which I could get its kinetic energy. So reminding myself that kinetic energy is 1/2 mv squared, I could then go 1/2 and then the mass, 9.11 times 10 to the negative 31 kilograms. For the speed of light, I will do it as a percentage of the speed of light. So the speed of light is 3 times 10 to the 8th. And did they say 3%? Yeah, 3%. So I will go 0.03 and square it. And since I'm doing a speed in meters per second, I need to do mass in kilograms, and so all of this would be energy in joules. So I want to always be careful about what units I'm using. So I'll do the speed first. So 0.03 times 3 times 10 to the 8th is about 1, 2, 3, 4, 5, 6. Yeah, so about a 9 times 10 to the 6th. And then I'll square that. So that by itself is a big number, but the mass is so small, 9.11 times 10 to the negative 31. And then a half of that makes it a little smaller. But I come up with a number of 3.69 times 10 to the 17th joules. And so that's its energy. And I want to use that to get to its wavelength. And if I did this, I would be making a big but common mistake, because that is the energy for the photon and how the energy of a photon is connected to its wavelength. That's not what I have. You might remember then from the lecture, I did this step where I said, let's multiply top and bottom by the mass. That way, in the top, I have mv, which is momentum. And de Broglie's hypothesis, I'll put it here, was the momentum is h over the wavelength. And so this would become Planck's constant squared over the wavelength squared. So I'm going to go h squared over 2m times the wavelength squared. Which now, if I put in all of these numbers, 6.63 times 10 to the negative 34, and I square it, and 2 over times 9.11 times 10 to the negative 31, and lambda squared, I can then take quite a few steps, and maybe to save a little time, maybe I'll just kind of move things around in my mind here. Let me do this. Let me imagine taking this lambda squared and moving it over to here. And then I'll take this number and move it over to here. So let me get all three of these numbers down in the denominator. So I already have this one in my calculator. So I'll just go that number times a 2, and then that number times a 9.11 times 10 to the negative 31, and I'll hit enter. And so that's in the bottom right there. So let me take the top and divide it by this answer. Okay, so 6.63 times 10 to the negative 34 and square it, and then divide that by the last answer. Okay, so I put all my numbers together and moved lambda squared. So over here in my mind, I've got lambda squared. One last step. I wouldn't encourage you to try to do that much math in one step. But if I didn't make any mistakes, I get a wavelength of 8.09 times 10 to the negative 11 meters. You might even call that .09 times 10 to the minus 2 nanometers, which you might call 0.0809 nanometers. And I just wanted to, again, I've done this a lot, but one more time at least, say, look, that is an enormously small wavelength. And so this particular electron, that's really not going that fast for an electron, 3% the speed of light. I don't even have to use relativistic effects. Could then be used to measure things well under the size of a nanometer. It just doesn't have that much energy. This might be enough to destroy something, so I probably couldn't use an electron microscope in that much detail. But I could probably use it to see things that are the size of a nanometer or so, or even a fraction of a nanometer. Well, that is a fraction of a nanometer. And that's what I wanted to illustrate. All right, one more here. 56 then says, what is, maybe I'll put it here on the board. And so 56 says, what is the wavelength of an electron that has been accelerated through a 30,000 volt potential difference, as is common in an old school CRT TV screen? All right. Notice again that they're asking us for the wavelength of the electron, and they're giving us the energy. And so, again, this is where I want to be careful, make sure I use the right equation, and use the one for electrons. But I'll start with the energy. You might say the kinetic energy is being accelerated by the accelerating voltage, and like the problem I did a little earlier, let me not redraw it, but this would be the electron gun, and so you would have the electrons boiled off and then accelerated. And so when they say that you put the charge of the electron, let's just put E, and then they say this is 30,000 volts, that way I can quickly just say that this electron has an energy of 30,000 electron volts. You might just call it 30 keV. That's how much energy it has. So again, this is the nice thing about working with an electron volt and electrons, because the charge times voltage is the energy in electron volts. So if you know you accelerate it by 1 volt, you get 1 electron volt. That was our definition of an electron volt, the energy gained by 1 electron when it is accelerated by 1 volt. And so in this case, we have 30,000 volts, so we must have 30,000 electron volts. So there is the energy. However, it might be wise to convert this, and I'll put it here, 30,000 electron volts into joules. And so 1.602 times 10 to the negative 19 over 1 here. Because when I go to calculate the kinetic energy, I don't want to use that 1240. That was the magical pattern and number and equation for photons. And so I want to use this one. So this would be h squared over 2m lambda squared. And again, since we're near the end, forgive me, I'll try to go a little quicker and just kind of do this math in my head. But what I'm going to go ahead and do is imagine moving the lambda squared to this side and then this energy underneath. So let me get that number first. So that number would be 30,000 times 1.602 times 10 to the negative 19. So that's that number. And I'm going to imagine moving it over here and multiply it by a 2 and an m. So times a 2 and times an m, which is 9.11 times 10 to the negative 31. So that's the number in the denominator. And I'll leave that in my calculator. But let me go back to the numerator, remembering it's this right here from the last problem. 6.63 times 10 to the negative 34 and square it. So when I divide by my last answer, I get a quotient that would be the wavelength on this side squared. And so one last step by taking the square root gives me a wavelength of 709 times 10 to the negative 12. And I've done everything in the base units, and so this must be meters. And then we can convert it to nanometers and talk about it, but I think this would be a good place then to say, hey, let's call this video a wrap. We did some really great stuff along there. Introduction to quantum mechanics. Hopefully you got the thinking of Planck and his hypothesis, Einstein's boldness, how it explained the photoelectric effect, how Compton added the momentum into the picture, how now we can think of both electrons and photons as either a wave or a particle, so their duality, what I like to call a wavicle, and so they each have the dual nature. And so we just got to be careful as we're looking at a photon versus an electron. They have a different equation for the energy, but the same one for the momentum. Easy mistake to mess up. But the biggest thing was we see now why there is even quantum mechanics. We see, as I think you saw at the end of the lecture, how a standing wave pattern would be quantized with our acoustic. It had nothing to do with atoms, electrons, or chemistry, or anything of that. We just had the frequencies quantized in the acoustic part of it. I think that was chapter 7 back in, or 17 back in Physics 110. And so we are seeing the same reason that was quantized is the same reason nature is quantized, because electrons are made out of waves, and we got to start treating them as waves. All right, well, I'll say bye for now, and we will move on to the next chapter tomorrow. All right, take care, everyone.